Yeah, it's very close. Be careful in what you say.
Do you guys want this extra chair removed? You want me to remove this extra chair or you want to keep it? Whatever you prefer. It's just if it's in the way for you. Okay, okay, so yeah.
May I have everyone's attention? May I have everyone's attention? Thank you. We're about to start, okay? I'll be chairing this fight, co-chairing this fight. My name is Rusty, and I'm a OSU alumni. I did my PhD here. I graduated in physics. I graduated a year ago. I'm currently working in finance. And it was back in 2017 when I did IPT my first time. I did it with Venezuela and in Sweden, Chalmers. And it was a great experience. And it got stuck in my head. And I was like, I want to do this again. And I come here to OSU. And I tried and assembled a team. So we went to France, 2023, I believe. No, 2022. No, 3, yes. Then we repeated, 2024. We made it to the semifinals. Then with OSU. Then we did 2025, and here we are in OSU doing IPT. I think it's a wonderful moment. I'm very proud of IPT and Oklahoma State University. I think this is a great place to be. For those of you coming to the United States, Oklahoma is a very special place to be at. Not many people have the chance to come here, and I think it's very unique and special. So with that, I'm going to introduce my co-chair, Deborah.
So, hello everyone, my name is Deborah. I'm a student right now. I'm doing my master's at the University of Warsaw in theoretical physics. I managed to win the IPT in 2023 with the best team, like Team Poland. Yes, Team Poland. So since 2023, I'm in the IPT. I joined the Execom it was the time between 2025 and 2026. And yeah, I just love IPT, and I'm so happy that I can be here again and again. And I would say good luck to you, and I will go to the Christos.
Good morning, everyone. My name is Christos Andrikopoulos. I am the Vice President of the Execom for the IPT. I have been with this tournament for many years now, my first tournament as a member being in 2018. I am doing my PhD currently in severe nuclear accidents, working with nuclear material. I will be a juror today, but for the start of this fight, I will also be a co-chair to help my co-chairs set up a very exciting physics captain's fight. But that we're gonna see later. I think it's high time that we introduce our jury members. And maybe we start with Christoph.
Hello, everyone. My name is Krzysztof Turzyński. I'm a professor of physics and the deputy dean for student affairs at the University of Warsaw Faculty of Physics. And my first IPT was in 2016. Over the years, I have seen many little dramas unfolding about winning and losing. But my impression, and this is my impression as a professor and as a teacher, is that the place that we are at now is a wonderful place to grow, to share, to communicate. And I'm personally implementing elements of the tournament in my teaching. And I just want to say that we have probably the highest concentration of people who think that physics is fun in the world here now in this room. So I just want to ask the participants to show us that physics can be even more fun than we think right now.
Hi everyone, I'm Maya, I'm a team lead of Team Croatia, and I'm second year PhD in Zagreb. I joined IPT in 2022, I think, in Colombia, and yes, so first time here, I fell in love with the whole tournament, with all the people that were really enjoying physics. I'm not going to repeat what Christoph said beautifully, and yes, I wish you all good luck in the finals and have a great fight. Thank you. Thank you.
Hello, everybody. My name is Ubirajara. I am from Federal University of Minas Gerais in Brazil. I'm a professor there. I work with biological physics. I came in the BPT, the Brazilian tournament, as a jury once in 2021, I think, 22. And when I saw the students performing and doing those physics problems, I got, wow, I have to get that to my university. We start to compete in the BPT, and we are like the 3 times Brazilian champions and fighting with you guys. So it's an amazing experience. I think everybody get to get this in the university for the students. It's great. So yeah, I'm happy to be here and hope you guys have a great fight. Okay, thank you.
Hello everyone, I'm Denise Christovan. I have been team leader of Team Germany for the last 3 years, and even before that, let's say around pandemic time, I was working actually with Team Brazil. I'm originally Brazilian. And I would say my history with this tournament is a bit old because, a long time ago, I'm not gonna say when, I was also a participant on the IPT. And basically when I saw a chance afterwards to join again this tournament, I could not pass on this. And I'm very, very happy to be here. Also, I am a postdoc at the Max Planck Institute for Solid State Research, and I work with spectroscopy and quantum materials. I hope you have a very nice fight. Good luck to everyone.
Hi guys, my name is Gergő Fehérvári. I'm team lead for Team Hungary. I'm doing industrial PhD, second year. And based on my grades, I did not expect to be in the jury today, but I thank for my team to put this pressure on me. For you guys, I wish you a fair and very much enjoyable fight.
Hi everyone, I'm also from Team Hungary. I'm actually now working in semiconductor industry, but I obtained my PhD in Budapest. And I maintained my contact to the university, and that's how I got this opportunity to be a team member, or not a team member, but accompany these guys. So thank you very much for your welcoming here, and good luck.
Hello everyone, my name is Frederik Durhus. I'm a postdoctoral researcher at the Technical University of Denmark, and I joined IPT back in 2018, same year as several of my colleagues. And it has given me some of the best experiences of my student years, but it has also really shaped the way I do research, the way I decide how to approach a problem. And one of my good friends, Joachim, recently got a PhD project in an IPT problem, the magnetic levitation thing from Paris, which I'm helping with. So in that sense, I never stopped working on IPT problems, and it has really been a fantastic part of my life, and I hope you will have similar experiences. And good luck today.
Thank you. So, as I was saying, as alumni, coming back here brings me some nostalgia. And, you know, Oklahoma is famous for different things. Oh, sorry.
Well, before we go forth with your touching tale of Oklahoma life, maybe we need to introduce our teams. Let's start with...
Hey, I am Silvan, from team captain of Team Switzerland, and with me today I have Hannes, Alex, Moritz, Rafael, and Hervé. I'm sorry. You might notice I'm a bit nervous to participate in the finals. I'm so happy for all my team and all the members of Team Switzerland that brought us here to the finals, and I'm looking forward so much to having this amazing fight with you.
And may we proceed?
Hello everyone, I'm Jade for Team Friends. This is Joris, Mathieu, Antoine, Adrien, and Tristan. And we are really happy to be here to fight the semifinals, finals, sorry. And we are very looking to this fight with you. Good luck to everyone, thank you.
And last but not least,
Hello, my name is Daniil Kharitonov. We are Empirica, Team APT. Those are colleagues who are here with me. It's Maxim, Artyom, Sofia, and there are colleagues that are supporting us from our country via translation. It's Karina and Vasily, and our team leader, Alexei. Thank you. Have a nice Friday.
Thanks to all the teams for being here. Thanks to all the teams who also participated so far. We have seen amazing fights, and we're getting ready now for one of the greatest fights of the tournament. This is where the tension rises. This is where we see the most amazing physics. I think, Rosti, you and I are both so decided, and Deborah, like, so excited, right? But before that, we really need to decide who goes first, second, like, you know, this little choosing we do.
Yeah.
So, Rosti.
What's the name? Captain's fight?
Captain's fight, I think it's called, yes. But before we go to that, Rosti, I do have a complaint. Like, I love the physics. This tournament has shaped my academic career, as all the jurors said. But I have a complaint from the LOC. You promised that we would have like tornado warnings and running to the shelters. None of that has happened yet. I haven't seen the wind blow. Isn't that Oklahoma where the wind comes sweeping down the plain? What about you? What about when you were living here? Did you see any tornadoes?
Okay, this week has been windy, but well, when I lived here, I never saw a tornado, Christos.
There's no way. We need to do something about that. I mean, wait. Isn't this what we do at the APT all the time, right? That we take problems from everyday life and we somehow, you know, condense them into something we can work in the lab. And yes, sure, we take some approximations here and there, like the spherical cow approximation. You know, you have a cow, you have to condense it back into a sphere. Or you need to figure out how to put a PowerPoint on screen. This is the mark of being close to being a professor, I think.
All right.
So let's slowly go into the captain's fight. We will start with the practical captain's fight and then continue with theoretical captain's fight. How it will be is that the team who wins the practical captain's fight will get 2 points. The second team in line will get 1 point. The third team will get 0 points. And 1 point will be awarded to the winners of the theoretical captain's fight. And with that, may we see how we may coalesce this tornado problem. So you will have 3 minutes to answer the following question. Now, this will be the practical. We're going to set it up on your table. We just wanted to present it first. Take your time. Be relaxed.
Yes, we're going to put the materials first on the table. After we finish reading the statement of the problem, you will be able to start, okay? And then you'll have the 3 minutes. So let's distribute the materials.
Let me double check. Looks like it. Looks like it's running. Okay. So now that the materials have been set on the table, may we go to the description of the task you're going to have at hand. Now, if you remember our semifinals, we learned a little bit about the pinto bean, a beloved seed that exists here in Oklahoma. Oklahoma is also famous for something else, our tornadoes, their tornadoes. Your challenge is to recreate a tornado capable of lifting the non-spherical pinto bean cow approximation that we have added into your bottles. You are given a bottle containing water and the pinto bean placed at the bottom. You need to create a tornado inside the bottle and lift the bean as high as possible. You may use any of the provided substances we have in little cups. We have salt, we have corn syrup, we have plain water. But you may not remove any contents from the bottle or lift or tilt the bottle from your table. Doing such may lead to disqualification from this captain's fight. A team member must record the entire attempt with their camera, their phone camera, positioned to minimize parallax. As you will notice on the side of your bottle, there are markings where we can judge and estimate the height the bean reached. You need to submit a result. To submit your result, you need to show us the video and the specific frame where the bean reaches its maximum height as you determine it. Teams will be ranked by the maximum height achieved, and ties will be broken by submission time. So if you believe that you have reached the highest you can go very fast, take that video off, pause it, come to us, show us the frame that it has reached, we count it, and you get your score for this fight. And with that, I think all the rules have been explained. Me and my coaches are gonna walk around while you're attempting your fight to supervise that the rules are not broken. And best of luck. Your time begins now. Yes, you can do it like this. One and a half minutes remaining. Teams, almost 30 seconds are remaining for you to bring us a picture with your highest achieve the height? So, time is up. May I see your results, please?
Yep. That one and 90. That was the highest.
So 8? Team IPT has an 8. Who has the results ready? $11.5 for Team Switzerland. What about Team France? Do you have your results? 6.5. 6, 7. I'm sorry. Therefore, I think Team Switzerland gets 2 points and wins this fight. Team IPT gets 1 point, second, and Team France gets 2 points. 0 points, sorry, yes. Points. What can I say, my friend? Now I am complete. Now I can leave this place and say that I have seen not 1 tornado, but 3. And whoa, what impressive tornadoes they were. But you know, as I made this small reference to a meme before, I realized that, Rosti, we've been to this tournament for too long, man. We're becoming out of touch. We're becoming what, you know, the young people would say, boomers. And you know, I think this place, Oklahoma, the Stillwater, has a lake for us.
It does.
So maybe we see our theoretical captain's fight. You will have 1 minute to answer the following question.
We're gonna wait. Okay.
Estimate the evaporation rate of Boomer Lake on a dry, sunny day. Your time starts now. Yeah, this is a captain's only calculation, please.
You have 30 seconds. Remember to box your final answer. Time's
So
up.
pencils down, and may we get your results, please?
Can you write it down? Yeah. Please, please. We're going to announce the answers from the teams. So for Switzerland, we have 10 to the power minus 2 kilograms per second. Team IPT, 0.2 kilograms per second. And France, 3.5 times 10.
10?
10.
All right. Okay, may we see the answer? Evaporation per square meter on a dry day, about 4 millimeters per day. The area of Boomer Lake is 1 square kilometer. So it's 10 to the power of 3 cubic meters per day with a mass of 12 kilograms per second.
So this is out. No units.
No, it has units.
They didn't write units.
Yeah, but in the description we said in kilograms per second.
Okay.
So the 0.2 goes first, the first 5, and then the 0.01. Therefore, Team IPT gets the point being closest. Can we get some calculation from our Hexacom team? We need the VAR. I always wanted to do this. Yeah, we know math. We are physicists.
Okay. All right. We have a third fight. Okay. So one thing I do like every day, I used to do more often than now. When I was a student, people ask me, "Oh, what do you study?" I say physics. Their reaction is always like, "What?" And they're like, "What do a physicist do?" And it's like, well, pretty much kind of everything. I think the word physics, Christos, you might help me with this one, because it comes from the Greek, maybe physika?
I think it's quite Greek, yes. Referring to all natural things, basically.
So basically the universe, and that includes everything in the universe. So one of the, I'm working now in the finance industry, and one of the things that people, don't tend to relate physicists with that, but my manager is a physicist, my manager is a physicist, and so on until a certain point. And I want to take this time to say thank you to our sponsors. Yes, okay. The following fight was inspired in that both of our sponsors are great hedge funds, so we want to say thank you to them. Without their support, this won't be possible. I think it's obvious to mention also, we would like to thank OSU. They also help a lot, right? But this particular fight is inspired in finance. Teams may use their laptops. They can work together. They cannot use AI. Any variation of it. You also can solve it with pen and paper. It's up to you what you want to do. okay? You can even estimate it. There are many different ways of solving this problem, like any problem, I guess. So, Christos?
Yes, let's see.
So, the equation below is a commonly used model to predict the value of a stock at a certain time t. Given an initial stock price of $55, a strike price of $60, and a volatility of 0.29, estimate the price of a European call that matures in 1 year. Use the expressions below to determine the value V, where WT is a normal distributed random variable with a mean 0 and variance t. There you have the equation, you have the expectation value there V. There is a hint that you can even solve this with a Monte Carlo algorithm. AI is not allowed. So your time starts now.
Two and a half minutes remaining. One minute remaining. 30 seconds remaining. Five, four, three, two. Your time is up. Please hand in your answers. Do we need units? Is it in Japanese yen?
We can check who might go broke or no. If it's a good buy or no. Will you buy it, Christos? For how much? Okay, so the answers are for Switzerland, we have $12. For Team IPT, we have $0.1. And for France, we have $20. So $4.5, $4.4. So that leaves us with I think Switzerland, right? Okay, so Switzerland, IPT? Yeah, look scale. Yes. Huh? Yes, that's all. So in that case, 12 is first, right? Yes. Yes, Switzerland's first. Then leave us with, well, it doesn't matter.
And that concludes our captain's fight. Maybe we put some money in the stock market after all. And let's hand the mic to Deborah, our coacher, who will tally the points and announce the winner.
Thank you. So, 2 plus 1 is 3. We have 1 and 1. Oh, so we have a tie right here.
Were we not completely unprepared for such an occasion? Yeah. I guess we have to go to captain's fight?
Yes.
Amazing.
Amazing. Another captain's fight for Team IPT and Team Friends. Amazing.
And because so terrible in our preparation are we that we were completely unprepared. We have prepared a very special captain's fight that draws back to an occasion when we started 2018 our existence in IPT. And that time it happened in Russia, and a tiebreaker was desperately needed. Tiebreakers had been exhausted, so we asked our members to name Russian physicists. Now we do the opposite. We will name the teams who participate in the tiebreaker to start naming American physicists. So, born in the US, yes. You have 2 minutes to create a list, and the people with the more correct people in the team with the more correct people in the list wins the captain's fight.
30 seconds left.
Three, two, one, time. We're going to tally the physicist.
So, the team IPT got 3 names and the team Friends got 4 names. Congratulations. And we have, right now, the second place will be Team Friends and the third, the IPT. So, I'm starting with Team Switzerland. In which order would you like to choose? We want to choose second. Okay. Now I'm going to Team Friends. In which order would you like to choose? Okay, Team Friends would like to choose first, and the Team IPT would choose third. So please, welcome Team Friends to the stage. Team Switzerland. And the Team IPT, you have one special... Oh, the special place for you.
Okay, so reporter, you have 5 minutes to prepare. Remember to write your names in the board, please. Names in the board. To speak with the microphone because it's very
Ramène un autre adaptateur.
Turn it up, please. Whenever you're ready.
Non mais les gars, il faut 2 adaptateurs.
Non, c'est bon, c'est bon.
Ramène un deuxième morceau. Tu le colles à ta bouche. Tu colles à ton bouche. Yeah, we got 2 minutes.
De quoi?
I believe I am ready.
I might start.
Can you guys
You
hear me?
ready?
Is it okay?
Ready?
Yeah.
Okay.
Go. Dear members of the jury, dear audience, today I'll be presenting subject number 3 of the International Physics Tournament, Ping Pong Balls Cannon. For this subject, we are to construct a mechanical cannon and optimize the different parameters to launch a ping pong ball as far as possible. We are also not to use any explosives or compressed gas. Finally, we are to discuss the trade-off between precision and distance. So going into this, we had ideas for a lot of different designs, going with some more continuous flywheel-based designs to a more impulse-based design. We decided to go for, before discussing the design, we first have to discuss the theory, because we have to know if we can properly model and simulate the trajectories of our ping pong balls. So, we take into account the ball's velocity and the ball's rotation, and we look at the different forces at play. So we take into account gravity, of course, the lift force, the drag force, and we also take into account the rotational drag that will slow the ball's rotation down as it goes through the air. These expressions are pretty simple, but the complicated parts are the coefficients, which vary in sometimes non-intuitive ways. So for the rotational drag coefficient, we based ourselves on Tsuji and Mugarama's paper from 2002 that described the rotational drag coefficient as a function of the rotational Reynolds number. For the lift and drag coefficient, however, it's a bit more complicated. In Tsuji and Mugarama's paper, they assume that the drag coefficient does not depend on rotation, which is based on a model by Morsey and Alexander from 1972 for non-spinning spheres. And they assume that the lift coefficient is capped at 0.5 and then linearly augments with rotation. However, this does not work at high speeds and high rotations. And to understand this, we have to introduce a new parameter, the spin ratio. The spin ratio is defined as the ball's equatorial rotational speed over the velocity. At particularly high spin ratios, the drag coefficient will actually drop, and so it will depend on rotation.
Similarly, the lift coefficient, although it does increase with rotation as expected, will eventually drop and for perfectly smooth spheres even go negative, which seems very counterintuitive. But it means that our model is not perfectly, this model is not perfectly adapted. In the article by Kim Jae and colleagues, we get an intuition of why this happens. The ball's rotation reduces the size of the wake behind the ball as it flies through the air, which reduces the drag, and it also shifts the position of the vortices behind the ball, which means the lift forces go in a different direction. So for our ping pong balls, which are not perfectly smooth spheres, we based ourselves on Roland Seidel's article from 1992, which plots the drag coefficient and the lift coefficient as a function of the spin parameter and in different rotational regimes. We inputted these graphs into Python and then used linear interpolation in order to determine the drag coefficient and the lift coefficient at a range of different velocities and different rotations. And so with this, we are able to get the drag and the lift coefficient as a function of spin parameter and rotation, and as a function of speed and rotation. Now, all we have to do is integrate the trajectory using, for example, the RK4 method, and we are able, just from the velocity and the rotation and the different launch characteristics like the launch angle, to get the trajectory of the ping pong ball. Using Richardson extrapolation, we can guarantee that with the time step we chose, which is 10 to the negative 4 seconds, we deviate from the real mathematical trajectory by no more than 2 millimeters. So let's look at the different designs we explored. Firstly, we built kind of a siege weapon. We had a giant crossbow with steel cables and a traction wheel that was intended to induce spin in the ball. We built this cannon and tested it in our school. And the results were impressive. We were able to get 13.8 meters, but we weren't able to properly control the rotation or properly control the distance, so our precision was really bad. So we decided to spend the rest of our time focusing on a different design, a flywheel-based design. Okay, it works. So inspired by a baseball pitching machine, for example. So our design, this is our design. We have a 24-volt, 16 amps motor that powers, with a belt, 2 flywheels that spin in opposite directions. And by changing the gear ratio, we can change the rotational speeds of the 2 flywheels. And this allows us to precisely control, assuming there is no slip, the rotation of the ball and the exit velocity of the ball. So the exit velocity of the ball and the rotation depend on the speed at the surface of the flywheels, and these can be determined solely with the flywheel's rotational speed and the gear ratio. So we machined these different flywheels and moved the, let me just move the cursor out of the way. We machined these different flywheels and 3D printed the different components and used the 3D printed gear ratios in order to adapt the flywheel's rotational speed. The first experiment we did was we tried to characterize the motor. So here we have the flywheel's rotational speed as a function of voltage, and as you can see, we have a really good linear fit. This means that the resistive torque on the motor stays constant with voltage, and that effects like air resistance seem to be negligible in this regime. This is really good for us because it means that solely with the motor's voltage and the gear ratio, we can precisely determine the ball's speed and rotation, assuming no slip. But is there no slip? Well, with the videos we took, we were able to confirm, within a certain range of uncertainties, that the no slip condition was verified for each of our tests. Now, let's try to do some simulations to see how accurate our model really is. We have different sets of trials at different voltages. So here we have a trial at 5 volts, 8 volts, and 11 volts. And we measured the distances using a tracker and taking into account perspective as well, and plot then the simulation. And I want to emphasize here that the simulations solely take into account voltage, cannon position, and gear ratio, nothing else. And despite this, we still get really good predictions of the distance reached. We also tested this at the extreme limits of our cannon. So here, the ball is leaving the cannon at 26 meters per second and is spinning at over 60 times per second. And despite this, our model is still able to accurately predict the trajectory and predicts a distance that falls within the standard deviation of our experiments. Now let's look at the different parameters at play. The flywheel speed clearly just needs to be maximized. The gear ratio, it's not that clear because you can trade off speed for rotation and that might be preferable in some cases. Same for the launch angle. Unless we simulate the whole trajectory, it's very difficult to know what the accurate launch angle actually is. The height we decided to fix at 1 meter because it did not seem to us important to just see how high we can get the cannon, because obviously that would be the best solution. And as for the ball structure, we decided not to change it because otherwise you could just add weight and add dimples and you would have a golf ball. So we decided that part of this subject was the difficulty of a ping pong ball's drag coefficient. So we have to find the best gear ratio and the best launch angle to maximize the distance for different flywheel speeds. To do this is a 2D optimization problem. We don't want gradient descent because we would be stuck in a local minimum, so we use differential evolution, which allows us to find the global minimum using an evolutionary algorithm. So we plotted this, and we were able to obtain the bottom, this graph, which I will explain. On the bottom here, we have the flywheel rotational speed, and we have the optimal gear ratio and the optimal distance for each flywheel rotational, and the optimal gear ratio and the optimal angle for each rotational speed. And so we can see that starting at about 15 volts, it actually becomes preferable to trade off speed for rotation because of the lift of the Magnus effect. And so now let's maximize our shot and have the best shot possible. So our motor's maximum rated voltage is 24 volts. At this voltage, we reach a speed of 372 radians per second. That corresponds to a ratio of 0.95 and a launch angle of 25 degrees. So what happens if we take all these parameters and we put them together into one experiment? We get this magnificent shot that goes all the way at a surprising distance of 17.67 meters. That was our maximum. And the average on the 4 shots that we did was 17.25 meters. I want to mention that we can fire these in quick succession because the design allows us to feed multiple ping pong balls in the cannon and fire them quickly, one after the other. I also want to emphasize how crazy things are getting in this cannon. Here, the flywheels are rotating at over 60 times per second. This is in slow motion. So we are really reaching extreme regimes. Next, let's discuss the trade-off between distance and precision. There are a lot of variances in the sources of the imprecision. There is imperfections in the ball, imperfections in the flywheel, in the coating of the flywheel, and inconsistencies in the launch angles that we observed. There could also be some slight slipping at high speeds because of the frame rate, we aren't able to guarantee the no-slip condition for very high launch speeds. So we decided to plot the precision, which we defined as the standard uncertainty in our trials, as a function of distance. And as you can see, it increases, but very slightly with distance. It still says very tightly grouped, except for this one outlier here, which corresponds to a ratio of 1. And so to explain this, we can see that a ratio of 1 corresponds to no spin at all. And if those of you who play baseball or soccer would know that a ball with no spin actually behaves very erratically. This is a well-known phenomenon in sports physics. It's the phenomenon behind a knuckleball in baseball and behind crazy soccer shots. And the literature tells us that this happens when the spin parameter is very low, below 0.1. So to guarantee that we have a spin-stabilized trajectory, we would need a spin parameter that is above 0.1. And this corresponds to a maximum distance of 16.82 meters. So what we can see here, discussing the distance versus precision trade-off, is that we can sacrifice about a meter of maximum distance in order to have a more precise trajectory. And the reason, by the way, for this instability is because the vortices are asymmetric and create erratic lift forces. So to conclude, we were able to construct a cannon that launched the ball at an impressive distance of 17.67 meters, and we were able to discuss the trade-off between precision and distance, and also have a lot of fun while doing it. Thank you very much.
Now it's time for clarification questions from the opponent.
Yes, hello, thank you. Could you bring us back to page 24, please?
44?
24.
24.
Did you measure the launch speed of the ball? The speed of the cannon as it leaves the muzzle.
In this trial, no.
Did you measure it in general?
In general, yes.
Okay. What was it? What was your maximum launch speed, for example?
As I mentioned, the ball can reach about 30 meters per second. This was earlier. Using tracker, and I can go into more detail of the different problems with that later.
Could we please see the formulas on slide 26 again, on the top right?
Yes.
The C4, what's that again?
So this is how you calculate. Okay, I won't go into too much detail, but if you assume that the distance distribution is a bell curve, is a normal distribution, then this is the uncertainty on the uncertainty based on the number of trials.
Thanks.
Did I understand correctly that the maximal speed at which you can spin your flywheels is limited by the voltage of your motor?
Yes.
Then on slide 5, please. Okay, so the CD is the top curves and the CL is the bottom curves, and that's the one.
On this graph, yes.
Yes, okay. And then on slide 17. Okay, and then on the next slide. Okay, thank you. Could you go back to the conclusion slide, please?
Oh, my bad.
Okay, perfect. Thank you.
Thank you. Now it's time for the opponent to prepare. Okay. Please, some silence for the teams. Please, some silence for the teams. Okay, thank you.
Okay, my name is Moritz. I'll be performing the opposition for Team Switzerland, and under the experiment ping pong ball cannon presented by France. First of all, I want to congratulate you. I think this is a really interesting experiment, and you achieved an amazing result. So good job so far. Problem statement: yes, well, we are asked to construct a mechanical cannon, and then we want to launch the ping pong ball as fast as possible, or like as far as possible, without breaking it. We should also discuss the trade-off between precision and air distance. Okay. So for the outline of the report it considered multiple approaches. So they started with a simple, like crossbow type setup, and then they pivoted to a flywheel setup. They modeled these things quite extensively. So they considered the drag, the lift coefficient, and the rotational drag. They also introduced the spin ratio as a way to model this. They integrated the equation of motions to get predictions of the trajectories, which was very nice. Yeah, with the first approach they had, they could reach a maximum distance of 13.8 meters. They identified that the biggest problem was that they could not control properly the rotation. And therefore they had poor precision and also couldn't make full use of the advantage introduced by the Magnus effect. For the second approach, they pivoted to flywheels, where they applied some voltage to a motor, and then they verified the gear ratio to obtain very precise rotation, with which they could fully control the parameters of their balls. They achieved very precise agreement with the numerical results. For the optimization, they performed an algorithm that was actually not gradient descent to optimize the launch angle and the gear ratio, and they achieved in the end a maximum distance of 17.67 meters. For the distance precision trade-off, they argued that this is mostly due to the variance of the imperfections in the ball, as well as the setup, and that they are able to sacrifice more of the ideal spin for more additional stabilization. Now, let's consider some strengths and weaknesses of the theory. So the strengths were mostly that they had like a very extensive model, and that also the model matched later quite well to the experiments. They highlighted the importance of spin ratio, which is quite a central parameter, and they optimized, they did a nice analysis of the optimal parameters. They did a very thorough error investigation, and they clarified the dependence of the spin parameter and the distance it can do for precision. For the weaknesses, we saw that the rotational drag coefficients were fully taken from paper, that there was no independent description of this, and also that there was only a qualitative explanation for the wake reduction effect for non-smooth rotating spheres. Furthermore, there was no mention of a critical drop of the drag coefficients as Reynolds number increases over a critical value, which we think would be interesting to explore further. On the experimental side, we really liked that they had multiple ideas to accelerate the ball, and then evaluated which one was giving them the best results. They had very high controllability of the parameters. They identified that the no-slip condition would be important, and they tested whether or not it is true, and their modeling in general was quite accurate. For the weaknesses, we saw no control for the confounding factors of the distance measurements in their hall. For example, there could be airflow or other effects. Furthermore, this is just one tiny caveat, but their precision fit did not intersect the origin, which it should, because if we shoot the ball at a distance of 0, there should be no imprecision on this. And finally, I think this is the most central point. Their setup eventually was limited by the motor. So I think, in my opinion, they didn't explore fully how far they could push the setup, because eventually the maximum distance they could achieve was just by, okay, how fast can we spin our wheels? What I think would be quite more interesting is how fast can we spin our wheels before the ball will break down due to this compression applied by the wheels. So for the further discussion topics, I think for the theory, we can maybe argue, we've seen your very nice simulations, or very nice optimization of the trajectory you can achieve. Maybe we can try to find some intuitive understanding of this optimal ratio between the energy which we can put into the speed, the linear speed, as well as the rotation. And furthermore, maybe we can think a little bit, what are the causes of the imprecision? Is this some parasitic spin we introduce, or is it fluctuations in the air in our hall? These would be interesting to explore. For the experiment, as I said, the most central point is limitation of the energy transfer to the ball by the motor voltage. Maybe let's try to explore what is the limit if we have a better motor. And then, furthermore, if we are in this limit, how can we optimize the transfer of energy to the ball, and how else can we reduce the drag on the ball? Maybe there's some more exotic ideas we could explore if we have the time. For example, we know it is not quite clear within this frame of the problem statement if we are allowed to perform some small modifications on the ping pong ball, but maybe if this is the case, we can think maybe there's some ways to do nice things about this. Okay, I think this is a nice framework for the discussion. I'd like to invite the reporter back on stage. Maybe we can start with the very first aspect. How can we intuitively understand the optimal ratio between the voltage and the spin we introduce?
So your first question was intuitively understanding the optimal ratio?
Right, so assume
Yeah.
that we have a limited amount of kinetic energy which we can impose on the ball.
Yes.
What is the optimal trade-off between introducing this into the spin or into the linear velocity?
Right, so, hold on. Let me go into, is it visible? Yes, it is. So this is the whole point of this graph, was to show the trade-off between, trading off velocity for rotation. And the way we can intuitively understand it is that the ping pong ball is very light, is very affected by drag. And so you can't expect that at one point adding more speed just barely adds any distance, but adding rotation can have that lift to carry it further. That's how you can intuitively understand how the lift force can help carry the ball along further.
I see this is, I understand this is mostly due to the fact that the drag scales quadratically in velocity, right? So like a small increase in velocity will have like a big effect on the drag. However, like if we just import this velocity or this energy into the spin, we just increase the lift force, so we have a longer trajectory without needing more velocity.
Right.
Very
Yeah.
nice, okay. Nice. So then, can you say maybe a little bit more about the causes of the imprecision? Like why do you observe this scattering of your final launching position around the mean?
Well, there's imperfections in the ball, first of all. So a ping pong ball has a logo on it that might not seem very significant, but it actually changes how the drag behaves, how the wake of the ball goes around it. The way our setup was designed, I don't think it was spinning at 60 hertz. Even with all the care in the world, it was still vibrating a little bit, so that definitely induced some inconsistencies in launch angle and in the different parameters. And of course, we're also limited by our technical precision, how we can't machine everything down to there's uncertainties on the size of the flywheels, on the size of the ratio, and etc.
Did you ever measure the spin of the ball coming out of the cannon?
Yes.
It's also in the direction which is not like in the direction where the spin axis would be aligned with the direction of motion.
Yes, so that actually worked really well. The spin axis was nearly all, as far as we could tell within the uncertainty of the tracking software, the spin axis was, the spin was purely backspin, is what I'm trying to say.
Nice, thank you so much. Maybe let's proceed to the experimental part. I think we can all agree this is, at heart, this is an engineering problem, right? So we really want to see how far can we push the distance in this case. I saw that you were eventually limited by the voltage of your motor. Why did you not choose to maybe try to find a different motor with which we could push the setup even higher?
So this is just a personal limitation. We did not have a stronger motor, and we did not have the resources or the time to find a stronger one. But this study is still applicable to higher voltages. So also another thing we could do, there's a lot of different optimizations in the Canon design. If you have two motors, you have a less resistive torque on the system.
Sorry, let's maybe go back to the point. I understand you couldn't really find a stronger motor.
Yes, sure.
Let's explore if you had a stronger motor. If you can spin
right.
the wheels as
Okay.
as you want. What are you limited
so
by?
actually, what we found is that we're limited by in our design at least, we are limited by the Canon first. What I mean by that is that the ball, the rubber coating on the flywheels seem to wear out faster than the ball itself, and we can actually calculate what amount of.
By wear out? Can you clarify?
Well, you can see on the photo here.
Yes.
There's as it shoots the ball out really fast, it digs into the rubber, and so that introduces problems, and over time will break the cannon.
Okay, but for a single shot, this should not be an issue, correct?
Well, even at high speeds, we did have problems where the cannon would snap, and
the cannon or the ball would snap?
The cannon.
Okay.
This was a part where the cannon sort of exploded, and we can calculate how much deformation we can put on the ball, so how much we can squeeze it. But if we're looking at other than that, if we're looking at when the ball will break from aerodynamic forces, for example, that's extremely fast. That's like Mach 1.5. So
I'm certain it will break due to the forces we apply during the kickoff of the ball.
Right, and so what I'm saying is that here, if we calculate the forces we apply when we compress the ball to launch it, it's about 50 newtons, which isn't close to the 150 newtons required, as we see in literature, to break the ball, to crack the ball.
Did you study this at all independently, or did you just assume the literature value of 150 newton?
We.
Now it's time for clarifying questions from the moderator. I remind you to get your microphone close enough, so, okay?
Okay, thank you for your presentation. Could you please move on to the 18th slide?
18th slide.
Yeah, and you measured the rotation speed. It was with the CV or how?
How we calculate the rotation speed?
Yeah, of the ball.
So yeah, so if I can clarify a little bit, we painted half the ball. Well, with a Sharpie we painted half the ball black so that we could track the rotation, and we did this over as much rotation, as much frames as possible to get the best precision.
Okay, wonderful. And there were also, you've mentioned some errors, not errors, like
uncertainties?
Deviations in the theory. I mean that, have you calculated it? What source of deviations do you include in your theory?
So in our theory, it's an exact theory. We have just exact drag coefficients and lift coefficients. So we don't have like random deviations in the theory. The random deviations we observe are in real life because nothing is absolutely perfect, and there's always, you know.
Okay, and have you measured how the initial launch angle deviates from experiment to experiment?
How the initial launch angle deviates?
Yeah.
Can you clarify the question?
Does it change from the experiment to experiment?
No. Maybe I'm not, but I don't think so.
Okay.
You have videos where the ball launches and video is a bit distorted. And have you accounted this, or you haven't
yes.
measured this? Yeah.
We have.
Okay.
All right, time's up. Now it's time for the moderator to prepare. Time's up.
Hello. Hello, my name is Daniil Kharitonov. I'm from Team MPT, and I will be moderating the solution for the problem number 3, ping pong ball cannon. The problem itself is quite engineering problem, and we need basically to construct a mechanical cannon that can launch ping pong ball to a distance as far as possible. And we also need to account accuracy and precision in our experiment. In the report was actually, by the porter, it was done a great job actually. They've extensively studied the theory of the process. They accounted, I believe, most of the forces, maybe all the forces that can be applicable. They got the theory proved with their experiments. They achieved actually a great distance of 70 meters with just 30 meters of initial ball velocity. And what they did is that they firstly created a ballista, which was not so with which they obtained not so great results due to lack of rotation of the ball. And the rotation that was shown is very important, in fact. And then they used tennis ball rotation with flywheels that accelerated ball even more, and even more rotated it so it would fly faster and further away. Opponent actually pointed out main points of the report. He he also, I believe, asked several important questions, in fact. Yeah, because though I believe that experimental investigation of drug coefficient was not necessary, like you can take the results from other people, from articles, also, but the questions about the actual limitation of the setup, I believe is far more interesting to investigate, because how far you can push the setup. Like if you have ideal, in a way, ideal results, ideal motor, is there a limit to what extent your theory is applicable, to what extent you can, how far basically you can launch a ball with all the materials you need. During the discussion, there was the several points were discussed, and the important of them, the most important are, in my opinion, precision access, because it was shown that precision factors, because it's basically about the limitations, and we can discuss it further. But the first questions I want to ask for both the opponent and the reporter: what would you do if you had what the first thing you would implement of your setup if you had better motor or better materials?
Yeah, I
what
think.
is the most important?
I think for the question, I think it is quite clear that currently we're limited by the motor and we need to overcome this. So what I would study in the first place is I take my better motor and then I try to somehow model a bit more extensively how much can we stress the ball before it will break down.
Mhm.
And then I will try to optimize my acceleration mechanism for achieving like maximal speed and maximal spin without exceeding this limit. So I would be interested in things like, for my wheel, what is the optimal coating of them, so that maybe there's some softness so that I don't stress the ball too much. What is the optimal radius of my wheel, so that maybe I can accelerate the ball over a longer time without compressing it too much in between. These are questions I would be interested in.
Okay, just to clarify this point about how far can you push it before you destroy the ball, in terms of tangential forces, those at least in our setup would damage the rubber coating on the cannons before it would damage the ball. And as for compression forces, we only need about 50 newtons in order to have a no-slip condition, which is far below the breaking point of the ball. So we feel like the limitation would still be the motor. Like you would need a really powerful motor to start breaking the ball.
I believe that, am I right that your question was about like the problem that actually if the ball moves too fast, it can break from air drag or something like that. Can it overcome, for example, sound speed?
It can, but that's when it starts to break. It's about Mach 1, according to literature, Mach 1.5. So that's really fast, and without compressed gas is, I would say, nearly impossible to get with a mechanical cannon. Maybe you prove me wrong.
If we're approaching this regime of like exceeding sound speed,
Yeah.
how do you think your entire modeling, does it still apply in this regime?
No, not at all, because all these tests are for trajectories. I mean, I can go back to Seidel's model, but by the way, when you say that these drag coefficients were not confirmed experimentally, these are not theoretical drag coefficients for spinning spheres. This is for a ping pong ball. This is specifically for a ping pong ball. So that is quite reassuring. And these are for speeds that go all the way up to 40 meters per second and rotations that go all the way up to 150 hertz. So this is within what we have in our test. But if we go further, of course, we would need a new model.
Just quick technical questions. Which rotation speeds of the ball did you obtain?
Well, the maximum we obtained with a ratio of 0.5 was about 67 hertz, or 68 hertz, I think. So that's about 68 times per second. And at that point, we start to enter the lift crisis, where the lift is actually not as powerful as you would expect it to be.
One more thing I would be interested in is, like, I think it's clear to everyone we want to reduce drag as much as possible.
Yep.
And I think there is some papers studying that there is some very critical drop-off of the drag coefficient as we
Yep.
exceed a certain Reynolds number. Did you investigate this at all?
Yeah, so the Reynolds number in our experiments is actually below the Reynolds number of the drag crisis. So, yeah, this is a famous paper by Achenbach, and it tells you maybe I'm not pronouncing that right, I'm sorry but this paper from 1972 details exactly when the drag crisis occurs for smooth spheres. And the Reynolds range we are in is actually the upper range of 10 to the power of 4.
So you're far away from this limit?
So we are far away from this limit, but that doesn't mean there isn't a drag crisis, because as spin increases, you actually enter the turbulent regime earlier. That's what I explained with the graph on the inverse Magus effect.
Can you confirm that you for sure exceeded this drag crisis limit?
Well, we can just look at the, let's see, what was it, slide 5? So we reached spin ratios that were in the range of, like we were close to the, yeah. I believe our spin ratios were contained between 0 and 1.5, so we perhaps were not fully within that drag crisis phase, because for that you need really high spin ratios for ping pong balls, but yeah.
Probably, I hope it's okay if we go back again to this kind of engineering aspect, because you said that the limiting factor in your setup is that the flywheel breaks down at some point if you go to too high speeds. What we were thinking of is if you could have like multiple flywheels such that you have kind of a pre-acceleration mechanism and you kind of accelerate the ball over multiple wheels such that the velocity difference is a little bit smaller. Do you think that is something that is feasible experimentally?
Well, we have the no-slip condition verified, so at that point the ball is accelerated to its final velocity and rotation, but it might help in easing the ball into the cannon. We didn't have the engineering capabilities or the equipment to implement that, but yes.
Yeah, that answers your question.
I mean, yes, I guess.
And I'm sorry, we got a question from Team IPT here.
Yeah, I believe that a big part of this problem is the measurement of accuracy, and you have done this, but I believe that you can elaborate with the opponent on how you can basically estimate the maximum. For example, give the fundamental limitation for this accuracy, because you have this all these turbulences after the ball, and I believe you can elaborate on this.
So the question is, just discuss the uncertainties?
Because you see, I believe that the accuracy question is important in the problem, because you have some turbulence, and can it influence, in fact, the ball movement? Is it random, or we can somehow describe it? And I'd love to hear both of your opinion on this.
Okay. Well, what we noticed was that we had a really tight grouping, despite, and this goes, so if, let me go back to the slide, but we had a, so yeah, as you can see on our 24 volts one, we have a spread of about 0.4 meters, and on our 5 volt one, it was about 0.1, so we only increase the inaccuracy about 30 centimeters, but we increase the distance, we multiply the distance by 8. So it seems like, at least with this setup, the accuracy really doesn't scale that much with a distance.
Yeah. Did you quantify? I mean, I think we're talking about precision here, right? Did you
Yeah.
quantify the precision only in the like direction of like flow, or also like in the perpendicular?
We did look at the lateral precision.
Yes.
This we did not have on video because we did not have enough cameras for that, and our measurements have more uncertainty, so that's why we didn't put it in the main presentation. But it actually is very similar to the graphs we obtained on the longitudinal precision.
So in general, it is isotropic, the spread around the mean of a landing position. Is it true?
To a certain extent. That we need more studies, because with the amount of trials we have really high imprecision.
That makes sense. That makes sense.
Hi. So I'd like to bring us back to this optimization problem, because you've mentioned multiple times that you're limited by the coating of your rubber flywheels. But I find that quite unsatisfactory. What if you had an indestructible coating? What is the absolute limit you can reach?
Well, if we had an indestructible coating, I mean, we did not study how far we could take the tangential forces before the ball would break. Theoretically, maybe you could find some results on that, but the fact is, in our setup, we were mainly limited by our canon, and so we could not push these studies, we could not experimentally confirm any of these factors, and it's not really, it wasn't really relevant for our optimization.
I think time's up, unfortunately.
Thank you very much. So I would like to thank my opponent and the moderator for this really good discussion. This subject was a ton of fun. It also raised a lot of questions in our school's hall, but it was really fun to optimize this problem and also to look at the theory, because I found out that drag and lift were much, much more complicated than I thought. So thank you very much.
Questions from the jury. We'll start with Christoph.
Yeah, sorry.
So this is a question that's sparked by the opponent's comment about the topics for discussion about other ways to discuss drag. So do you think, and this is the question to everyone, that is there that an ordinary ping pong ball can sustain all the forces, all the drag forces before it enters a full-scale drag crisis? I mean, like, is it even possible technically to give it a speed so we enter the drag crisis limit?
Yes, I think so, because this is observed in competitive ping pong ball, competitive table tennis. But, I don't know what I said there. But the ratios in competitive table tennis, the balls reach speeds of 40 meters per second, and they can actually do that with also some really high top spins of 150 hertz. And so at that point, you actually reach the turbulent drag crisis.
So
I wanted the answer from the opponent too.
Yes, so I can only confirm what was said. So this is for sure possible. We've also talked to some other people, and we've heard that it is like possible, even without spin, to accelerate the ball sufficiently much that it can overcome this drag crisis. And if you do this, you observe like a very nice jump in the maximum range which you can exceed with your cannon. So this is very interesting.
Yeah, in fact, just want to point out, like Mythbusters accelerated the ball up to, I believe, 1,500 kilometers in hour, and.
But they used compressed gas to do it. So.
They used compressed gas.
Okay, I have more of just a technical question because I might have not picked it up from your presentation. So, can you explain a bit more in detail how do you measure where did the ball fall? So it goes.
Oh yes,
like
we
this,
didn't go into it.
In this other direction.
But I use a software called Tracker to track the ball's position, and we take into account all the different effects. So hold on. So we correct for distortion, and we also correct for the different planes. So when we track, we usually have a reference length, and that one might not be exactly in the plane of the ball, and so we take that into account as well. We really did our homework for that.
From the video, you can track this dimension, right? But how can you track the other dimension?
The lateral dimension?
Yes.
That was done more visually, and so that's why we have such uncertainties. We used the tiles on the floor of the hall, and also compared it with the videos using perspective. But perspective has a lot of uncertainties because you're looking. I mean, in a few centimeters, you have a lot of you do a lot of ground.
All right, thank you.
Okay, if you could try your ball with the velocity you want and the spin you want for the three of you, there should be a limit of the distance that you can achieve with. I'm not worried about the device, like there should be some theoretical limit for the distance you can achieve throwing with the velocity you want and the spinning you want.
Mm-hmm. Yes, there should be. If you had a perfect cannon that could launch the ball, at extreme speeds, I think the most hard limit that would break it would be the breaking of the ball due to aerodynamic forces, which is at Mach 1.5. So at that point, I think you would reach insane distances, but yeah.
Yes, for sure. So I think, like as you pointed out, like if as soon as the ball leaves the cannon, if we abstract this part away, then we are fully characterized by the velocity in like x direction, velocity in y direction, and as well as the spin of this ball. And for sure, for each of these parameters, there can be like some limit. You pointed out correctly, like the ball will break at some point due to aerodynamic drag. I guess we can also say if we spin way too fast, the ball will disintegrate eventually. But yeah, I think like in this case, we're limited just by the strength of the ball eventually.
And I have nothing to add. Basically, the boss opponent and reporter said everything.
You should not get a terminal velocity very fast, or...
Yeah, in that case, if you, I mean, it's already striking. The difference between 16 and 18 meters, or 16 and 17 meters is really hard because the ball just slows down so incredibly fast.
So following up on Maya's question, maybe, am I correct in understanding that you think the lateral dimension, let's say, it's not as significantly important for the problem as the other one?
It is, but we thought that we put it in the appendix because our measures were not that accurate with it, and the lateral precision, we had some uncertainties with it. But it is an aspect you can consider. We focused on the longitudinal precision, but the lateral precision is, of course, an aspect to consider.
Could you quickly define the difference between precision and accuracy?
So we define precision as the standard deviation. Basically, we assume that if you launch a bunch of ping pong balls, you'll have a normal distribution, and that we define the standard deviation of that normal distribution to be the precision. And so if you do a limited number of trials, you estimate that theoretical standard deviation. And so that's the uncertainties on the graph, is how well we estimated this standard deviation, if that makes sense.
If anyone wants to add anything?
Yeah, and just to clarify, different than that is accuracy, which is just if we specify a target, how precisely can we hit it, and the precision is completely decoupled from any target hitting. You just take the mean of the aggregate mean of the balls you shoot.
Okay, thanks.
So I think the reporter argued that the logo on the ping pong ball has an effect on the properties of the ball. So the fact that it has a logo, it changes the behavior of the ball, right? So is it the correct way experimentally to add excess ink to the ball when you were examining the rotation?
To add a what?
Is it the correct way to add excess ink on the ball when you were tracking the rotation?
So for most of our trials, was just to see the rotation. For most of our trials, we used the new ping pong balls, especially because we were scared that the ping pong ball cannon would add dimples or change the geometry of the ball in subtle ways that we could not see.
Okay, so that was just for demonstration purposes.
Yes.
And you tracked, okay, cool. And as for testing your setup, I think you, I would like to understand the effect of the parameters. Like you say that there is uncertainty in the beginning. That's why we don't see a perfect match with the simulation. I can accept that, but could you think of some chaos engineering way of testing those uncertainties? So like making some part of your setup a little bit less defined to test the sensitivity of how it propagates through the launch.
So how could we evaluate these uncertainties through by changing the setup?
By putting a setup in an environment where you have control over one variable.
Right. I guess you could maybe control the angle with some sort of. Well, what you could do is you can track the angle, and so that allows you to sort of tell you to correct for that and see what the effect of that is. You could also maybe just change reset the rubber on the wheel every time to make sure you don't have any wear on it. Those are the ones that come to mind right now. Yeah.
Thank you. Can I have oh, no.
Also, maybe have a standard, like instead of a ping pong ball, just have a pure celluloid ball with no logo on it, so you can see how that changes those are what comes to mind.
My question would relate to precision again.
Mm-hmm.
So could you explain how the precision increases or decreases with the distance?
So we put a linear fit on the graph, but it's not certain that that's what the law actually is. We would need more trial to figure that out. It could be logarithmic. What we did notice was that it did increase slightly with distance, but it was surprisingly not very significant. Even though we multiply by 8 the distance, we only multiply by 2 the imprecision.
sorry, I just didn't get fully what's the picture behind it. So why?
Why?
Yes.
Well, to show the trade-off between distance and precision. To show that when you increase distance, the precision increases, or the precision decreases.
I see, but what's your theory behind it?
The theory behind this is that because of inconsistencies in the angle, for example, those would have a bigger effect the more distance you have. Similarly, if you have inconsistencies, like if there is some slight slipping of the ball, basically those effects compound the longer distance you have because you have a longer flight time. So that would explain why the precision would the imprecision would grow, if that makes sense.
Okay, I will stick a little bit to these precision questions, but I think we had a lot of theoretical discussions, so I will ask for a drawing exercise to the three of you. If you look from the top down to the tiles that are on the floor, can you draw the area where 95% of the balls will land? Did you understand what I'm requiring?
Can you repeat?
So you're looking from top down, the tiles where the floor.
The tiles, yeah.
Yes, where your ball lands. And if every ball that lands, make a small mark, what would be the shape of 95% of the balls that land? This shaded area, this shadow that will be created by all the balls that land. Will it be a circle? Will it be a cylinder? Can the three of you draw this shape? You use the Canon, and the image that we're looking now is if we're looking like a bird from top to bottom. So what Team Switzerland basically, the view that Team Switzerland is drawing, this type of view, is the floor plan.
Should I go ahead and explain? Or
yes, please.
Right, so this is like kind of what I was going at with one of my questions, if the distribution of the landing spots around the mean, if it's isotropic. And they said, yes, it is to some degree, but I mean, they didn't have sufficient measurements to distinguish between maybe a perfect circle or maybe something which is more like what I draw, because I mean, you need a super high number of measurements for this. So the reason why I choose to draw this shape is because, of course, as we saw, I mean, if we have some imprecision in the y angle here, as we saw, like for further flight paths, this will materialize stronger. So then we'll have more spread. I mean, in this case, we shoot from here, right? So if we are closer to our launching point, we have somewhat less imprecision in this direction than in this direction.
Thank you. Can the rest of the participants reply?
Okay, basically, it will. I believe it would be an ellipse, but with close to the circle one, because it can be less imperfection in the direction you are shooting a ball at. But I still believe that distribution, accuracy in the other dimension also matters a lot.
Thank you.
So if we had more trials, we could characterize this a little bit better. But the idea is that you would have an ellipse with the dimensions of the ellipse being the standard deviation of the longitudinal imperfections and the imprecision and the lateral imprecision. And these would depend on how much the different problems like slipping or angle inconsistencies influence the ball's flight path.
Thank you all very much.
Yes, could I get a slide with a sketch or image of the setup of the cannon?
Yep.
You mentioned the cannon sometimes breaking. Which part exactly is it that breaks and how?
So surprisingly, the belt and the gear ratios, even though they're 3D printed, are actually quite robust. There was very little wear on them, and we were able to keep them going all the time. What actually ended up breaking was the rubber coating on the flywheels, which with the centrifugal force would just fly off, despite gluing it with epoxy or whatever we tried. it would just end up snapping off. And I believe I have a photo of that at the very end. Yeah, right there. So you can see that what broke was the rubber coating on the flywheels. So then you can't guarantee the no-slip condition, and so you have to rebuild, re-glue that.
Thank you.
Well, it was a wonderful fight. Now it's time for the jury to place their marks. We won't show the grades, as usual. With that, please silence. Everyone, it's time now for the feedback from the jury. Do you want to start, Christoph?
Okay, so I want to say what's already been said in the discussion, that eventually this is mainly the engineering problem, because theoretically everything was solved in the literature, and I'm impressed by your thorough review of the literature that, I mean, directed your experiments very meaningfully. And I think that this was a very good presentation, and if I can say publicly on the record, that's going to stay with us forever on YouTube. What's wrong with it? I won't say anything. Now, I have a comment about the opponent and the moderator. So I think that there were a couple of points for discussion that were amiss, and the complaints about not performing own experiments, which certainly would have been worse than those reported in scientific literature. I think that this wasn't an interesting option for discussion. And also, and this is and I think that the efficiency optimization, which was once hinted at, also, I don't know why that was brought up. Also, I'm not sure if in the short discussion about precision, you made sure that you all understand the term in the same way, because what I got from the French presentation, and this was evident from the discussion that you meant precision as the ability of predicting the distance instead of hitting a particular point on the floor. And if you consider lateral deviations, this becomes a little different discussion, and we learned that only in the jury questions. So that's my take on what's happened.
So yes, I also want to say very beautiful presentation, very, very nice work from the reporter. For the opponent, I think you brought up this, so we saw in the jury questions, I think 80% of the questions were about this precision and accuracy, and I was kind of missing this in the discussion. You were mostly focusing on the optimization, and then the moderator came in, and there was actually a question from the team about this, and it kind of started. And but yes, all in all, a very nice fight. I think you all got good raise from all of us, but I think some things can be better, and yes, this is just a learning experience. Thank you.
Yeah, I liked a lot the setup, amazing, and I like the discussion. I would like to see more of the theoretical limits that you could achieve and go to a more physics of the thing. I don't think you cover everything, you guys, but you did a nice job, and I think the discussion was stuck in some points and could not flow a little bit, but otherwise, thank you so much.
So I don't have much to add actually compared to the comments I already made. I think maybe on the scientific side there were some aspects that were actually brought up, I think by the moderator probably, that you could have pushed further on your design, for example the number of wheels. But I would actually want to give some quick feedback on the discussion, the dynamics itself. I felt like you had very nice points to discuss, but because you were kind of talking one over the other a little bit and maybe just pausing more, it would be also interesting for us to be clear on what you're trying to get at, because at some points I was a bit like, okay, what is actually happening? So this is actually something that you guys can work on for the rest of the fight, so that's why I wanted to mention.
Yeah, I would have loved a little bit more analysis on this uncertainty stuff. I'm still, you perform some optimization on a very complex landscape, and for me, it's not trivial how that works when you have the physical realization of the system. And as for how the fights went, I really like the questions brought up by the opponent, and I would encourage all of you guys to try to take a step back and just look at all the work that you've done from a third-person perspective and not feel too emotionally connected to it. I know it's incredibly hard. I cannot imagine how it feels to stand there, but let's keep it friendly. Thank you.
Yeah, thank you. It was a very enjoyable fight. I agree with most of what was said, especially on the ambiguity of this precision and accuracy topic, and I think everything was said that I wanted to. So.
Yes, I agree that most of the comments have been iterated. I will say a personal comment maybe that I very much liked the setup. It showed that you have done exceedingly hard work to make it and to optimize it. And I think sometimes the discussion falters when you try to over-optimize an optimized setup already. I think what the discussion I would have loved to focus on is a bit more of the physics of all this that the jury members asked, the uncertainty. Maybe what I would have liked is what I asked for the drawing, to have like a 3D plot of how this cone of uncertainty, spreads. Something of the sort. But, and I think for the flow as well of the discussion, that maybe to the opponent, you can't be spread quite like the ping pong ball, you can spread in many directions, but maybe sometimes it's better to focus on one thing at a time, that we resolve it and that we understand it and that we move a bit forward. And maybe to the moderator as well to help out this from happening, to close this cone of uncertainty back into something that we want to focus on. So that's my comments for this one, but great job.
Yes, I agree with a lot of the comments. I would just like to say I quite like the opponent presentation. I think there was a good quantity of text. I've seen a lot of presentations this IPT where it feels like the opponent moderator have essentially done a brainstorm and are presenting all the points they could think of. I felt like the opponent actually got through his slides and still had time to present the discussion points properly. So I quite like that part.
All right. Thank you. So talking about precision and accuracy, we're going to have I want you to be very precise and accurate
for a 15-minute break, okay? It's gonna be here in the clock. So we're gonna start right when this clock starts, so especially for the teams in the jury, okay?
Check.
If you would like a second break, we should start soon. Otherwise, Christos have good ideas for breaks. You can ask him. I'm saying they can ask him. I'm not saying what it is. Please. No. Sorry. Okay. They have. I thought we. Okay, we're missing. Oh, Birajar is here, so Friedrich. Okay, so better get ready if we want a second break. Please. Thank you. Okay, now for this second round, Switzerland is gonna report, Team IPT is gonna pose, and France is gonna moderate. You have 5 minutes to prepare. Also, Team IPT, if you know who is going to post, you can write his name, so you don't have to like, be running. Also, I have a message for the teams. Remember to share the microphone. We have two, so whenever someone's going to talk, remember if you have a microphone and you are not talking, maybe someone else might need it, okay?
Please, some silence for the teams. Thank you.
Okay, I think we can start. Hello everyone, I'm Hannes and I'm going to present the problem number 8, the eddy current engine today. So in the video you can already see the eddy current engine that we built in our lab, so you can see these two aluminum discs that are rotating in opposite directions, and they're powered by this AC powered coil from below. So the problem statement asks us to build this engine, explain the phenomena, maximize the angular velocity of the discs and the efficiency of this engine. So let's first look at what's going on. So we have this coil, it's powered by an AC source that generates an alternating magnetic field. This leads to eddy currents that are being induced inside of these disks. They interact with the magnetic field and that leads to forces. These forces point in opposite directions, which makes the disks rotate. The question now is, where do these forces come from and why do they point in opposite directions? So this has already been discussed in literature a little bit, like in the Feynman lectures of physics. You can find a setup that is quite similar to ours, but he only gave a qualitative description of this problem, and there was no quantitative analysis. And so that's our job for the following. Okay, but let's first start with a phenomenological explanation of this. So first we look at how we can make a disk move when we have a magnetic field. And for that, we consider the most basic situation. We take a permanent magnet and we rotate it above this disk. And if you do the experiment in the lab, you can see that the disk is being dragged along with the movement of this magnet like this. So what's happening here? So if we move this magnet above our disk, what the disk sees is a magnetic field that varies in time. That means that we're going to induce some eddy currents in the disk, and from that we can also calculate the Lorentz force. So let's look at the left-hand side of this magnetic field. You can see that we get a contribution to the force on the right-hand side here, but there's also a contribution pointing to the negative side here. But note that we also have a spatial gradient of this magnetic field, which means that we get a net force pointing to the right. On the right-hand side of this magnet, this situation is quite similar. Okay. But in our lab, we don't have a permanent magnet, but what we have is this coil that is powered by our AC voltage source. So the question that arises is, how can we imitate this moving magnetic field of the permanent magnet with what we have in the lab? For that, we consider two poles, so this red pole and the blue pole, and note that they produce alternating fields, but the blue pole is phase shifted with respect to the red one, so it's lagging behind this red pole. There's this phase shift. We propose the following setup to actually look at this phenomenon in the lab. We also built this. Here you can see a picture. So the question is, did we observe a phase shift? And the answer is yes, we measured it. And as you can see, the secondary coil or pole is lagging behind the primary pole. So that confirms that. Okay, you can also give a symmetry argument for why we need this phase shift. So consider a perfectly symmetric situation where the two poles are producing magnetic fields that are in phase, then the situation is symmetric, so the force is 0. On the other hand, if we have the blue pole is lagging behind the red one, this is breaking the symmetry and that allows for a force pointing to the right-hand side. Okay, now let's go back to the setup that we had in the beginning with these two disks, and we have to explain why the physics that is happening in this two-disk setup is exactly the same as what we have for the newly proposed setup. So what's the most crucial point for our setup? It's that we have two regions in space that are separated, corresponding to the two poles, and that there's a phase shift between these two poles. So now if we have the two disks, what this disk on the top is doing, it's effectively shading part of our magnet, which also generates two regions in space with alternating magnetic fields that have a phase shift. Let's understand this a little bit better. So let's go back to the single disk setup. We associate some phases phi1 and phi2 to these two poles, and we have this phase shift delta phi. And what we observe is that the disk is always rotating towards the pole that is lagging behind. For the two-disk setup, you see that we have these overlapping regions in space, and there's one region where we have a double overlap of the two disks, and it turns out that there's also a phase shift between these red regions towards the blue region, which makes the disks rotate in opposite directions. Okay, now we want to model this theoretically, and as you can see, the most crucial point is that we have two regions in space, they have alternating magnetic fields, and there's a phase shift between the two. So if we want to model this, these are the factors that we want to concentrate on. So to make the geometry a little bit easier, we start with the setup on the right-hand side, and then later show why we can apply the theory to some extent to the two-disk setup as well. Okay, first thing we have to understand is how we get from a magnetic field to a current density. By induction, then we calculate the torque, and from that we derive the angular velocity using the equations of motion. So let's first start with induction. Note that we have to do is that we have to write down an ansatz for the magnetic field that we have, and we assume that the two poles are generating alternating magnetic fields, and in between we just interpolate linearly between these two poles. We can plug in some explicit expressions for that with two amplitudes B1 and B2 and some cosines plus this phase shift. Note that the most important parameters that we introduce here are this phase shift and the ratio between the two amplitudes gamma. Okay. Now, if we know Maxwell's equation and Ohm's law, we can derive an expression for the current density depending on the time derivative of the magnetic field. We can integrate this and find the current density in the y direction like this. So what we have now is a magnetic field in this shaded region as well as a current density. And as you remember, we can calculate the force density from this. And if we then calculate the torque, we get an expression that looks like this. Let's look at this expression a little bit more closely. So you can see that it's quite complicated, and there are these constants appearing. These constants, they depend on this ratio between the amplitudes gamma and also our phase shift. But what's more crucial is that we have two terms in this expression. One of it is a driving torque. Its sign depends on this phase shift. And the other one is an inductive drag term, which always opposes the motion. It's always a negative term, and it's slowing down our disk. We can rewrite this a little bit more easily like this. Okay. Now the last part is to find the angular velocity. For that we write down the equations of motion, and we have two contributions on the right-hand side, so this torque that we just calculated, and then there are also some friction terms. The question is, what is the friction? For that we propose the following model. If we just consider a freely rotating disk without a magnetic field, we have a constant drive friction, and then there's also a dynamic friction proportional to the angular velocity. We fitted a measurement with this model, and the fit is quite good, and it also allows us to extract these friction coefficients like that. So we can write down the full equations of motion, and in the stationary situation where the disk is rotating at a constant angular velocity, we find this expression for the angular velocity. Okay, how do we measure the angular velocity in the lab? So that's our setup, and what we do, we have a photodiode and this marker on the disk, and whenever this marker crosses the photodiode, we get a dip in the intensity. We measure this with an oscilloscope and calculate the frequency from there. Okay, let's look at some limits for the expression for the angular velocity that we got, and you see if we crank up the magnetic field, we find an asymptotic angular velocity that is only dependent on geometric parameters and the phase shift and this amplitude ratio, so like this. But then what we didn't include in our theory yet are boundary effects, so you can consider if we have these two poles and we move them very, very close to our boundary, this is going to effectively reduce the asymptotic velocity that we can reach because the coupling is just weaker. We measured this boundary parameter, and as you can see, it's always in the interval 0, 1, so this suppresses our asymptotic velocity that we get. Okay. Now we want to fit this full model to a measurement of the angular velocity depending on the magnetic field. And we have almost all ingredients, so we have these friction coefficients, but what's missing is the phase shift and the ratio between the amplitudes. So we measured the magnetic fields using two pickup coils at the poles of our setup, and here's the measurement. As you can see, we can extract the ratio between the two magnetic fields and also our phase shift. Now, this is a measurement that we took for a larger disk, And as you can see, if we fit our model, the fit looks quite nice, and we also get this asymptotic behavior for larger magnetic fields. We also performed the measurement for a smaller disk, and that's the behavior that we got. The fit is also quite good. So we have these two fitted parameters, and these phase shifts and the amplitude ratios are are measured. Okay. Now let's go back to the setup with the two disks that we had before. And what I want to show you is that the scaling is quite similar. You can see these two fits. But what we lose is the information about the geometry. So now let's turn to the optimization part. Our task is to maximize the angular velocity of the disk and also the efficiency of the engine. So let's start with the angular velocity. And the question is, what setup should we choose to maximize the angular velocity? As you can see here, for our setup with only a single disk, we get a higher angular velocity that asymptotically compared to the two disks. So what we want to choose for the optimization is this single disk setup. Okay. Now, it turns out that an interesting parameter to look at for the optimization of the angular velocity is this phase shift. You can see for a totally symmetric situation, as before, we get no force, so no angular velocity. On the other hand, if we have some non-zero phase shift, we get some force and also an angular velocity. But again, if the phase shift is minus pi, so they're completely in opposite phases, then we get, again, a symmetric situation where the force is zero. That means that there should be a maximum of the angular velocity somewhere in between. Now what we do is we take all our model and plug in the constants that we got from our fits, and this is the theoretical prediction for the angular velocity that we reach asymptotically for high magnetic fields, and here's where we measured. You see, we are quite off from the maximum, but what we can do actually is to manipulate this phase shift in the experiment. What we do is we introduce another shading coil at one of our poles, so that changes two things. It changes the phase shift as well as the amplitude ratio. So we get a new curve, and as you can see, this asymptotic angular velocity is being pushed up, but also our phase shift changes. So we get much, much closer to this optimal angular velocity. Okay, now this is a video of the highest angular velocity that we got. Let's go to the efficiency maximization of our engine. For that, what we have to do is we look at the situation where we want to pull up a constant load with our setup, so like a mass. That means that in our equations of motion, we have to include another term for the torque that is generated by this load. We define the efficiency, which is the power output over the losses plus the power output. The power output is just the torque times the angular velocity. The losses are mechanical friction plus some heat. The heat is generated by the eddy currents in our disk. This means that we get an efficiency curve depending on this magnetic field. So we want to know the magnetic field that we should power our engine at to get the optimal efficiency. So this is this efficiency curve that we can calculate for some specific typical load that we can use. And the reason why this curve looks like it looks is that if we have no angular velocity, of course the efficiency is zero because there's no power output. And on the other hand, if we increase the magnetic field even further, we are already in the saturated regime where we have the asymptotic angular velocity, so we just generate much more heat by these eddy currents. So that's why there's this maximum, and the efficiency is quite bad at under 1%. So to conclude, we explained the phenomena, wrote down a theory for it, we maximized this angular velocity, we manipulated the phase with this shading coil, and we calculated the curves that maximize the efficiency of the engine. So thank you so much for your attention.
Time for clarifying questions from the opponent.
Okay, have you studied the dependence on the frequency of your oscillating field?
We didn't change the frequency of the oscillating field. It was 50 hertz like European network frequency.
Okay, can you go to slide 29?
Oh, sorry. Yeah.
Like I see. Okay.
All good.
So, have you found exact explanation for initial phase shift in your ferrite core?
We have a qualitative explanation for that. Yes.
Okay. Can you open 34?
Yeah, was there any principal a difficulty to measure points just left and right?
What
or
do you mean,
just
like
didn't
left and right?
Huh?
What do you mean?
You have these points, and have you measured on deviate this phase difference?
So what we did is we measured the phase difference using these two pickup coils as described before in the presentation. And then what we do is we crank up the magnetic field as high as we can do, like we are limited by our maximal current. And then we measure what angular velocity that we get. And you see that these points are a little bit lower than the theoretical curves, and that's just because we are like almost in the saturated regime, but not quite. So yeah,
okay.
As high as we could go.
Thanks.
Okay, no more questions. Now it's time for the opponent to prepare.
Okay, hello everyone. My name is Maxim Bostrov, and I'm very glad to oppose this problem because I'm very fascinated about it. So I will be opposing the solution on problem number 8, eddy current engine, from Team Switzerland. The problem was about creating the eddy current engine and start explaining the effect and optimizing the angular velocity and efficiency. So let's revive what the reporter did. And I think they did a very great job because it's a very tough problem. So firstly, they give us very good explanation of phenomena. And since it's very complicated, I think they did it very well. Then they showed us the first setup and explain exactly why it's working and show how it's similar to one which was in the problem statement. Then they perform very deep investigation on what phase shift is in the system, what exactly they getting from any system. They measured many dependencies. Also, they studied like different limits of their system. So they account the heat which is generated by current engines, eddy currents. They studied how they can increase the angular velocity, the efficiency, and I think their theory completely match the experiment, and I really fascinated with that. So also they reach incredible speed, like 57 radians per second. So they made very good work on optimization. They presented a good idea of making a shading coil, which is making phase shift exactly what they want. And also they studied the distance between the poles and the size of a disk. Well, actually, I think one exact point of the whole problem was skipped, and it's a frequency, because I think it's a very relevant parameter, because when you increase frequency, your induction coefficient go up, and I think it can really improve the solution, because you can get better angular velocities and higher efficiency. So the points I want to discuss is what about frequency dependence? How actually it will work, and what the qualitative dependencies we can obtain. Also, since it's, I think, another limitation of a problem, when you higher the frequency, you get skin effect. So the currents go lower, and where is that exact limit? And also, as I mentioned, they have qualitative explanation of the phase shift in the ferrite core, and I want to discuss it, because for me it's not obvious why it's here on this not very long distance through the core. Also, maybe we, through this discussion, can come up for maybe some other qualitative explanation or analogy for the field, because I think the problem is very complicated and it can improve the understanding of the problem. So let's start the discussion.
Okay, yeah, thank you for the input. What you would start with?
Okay, I think we should start with frequency dependence.
Mm-hmm.
So, as we know, the electric field is proportional to the derivative of the magnetic field all the time. And since that, the frequency will be there. So,
yeah, exactly. At some point, you take a derivative of your magnetic field, and because you have a sine function with an omega in it, what you get out is some other omega dependence. And in fact, our formulas also show that. So If you look at this formula that we had for this torque that we get, you can see that it's actually proportional to, like this driving term is proportional to that omega that we get. And I think you also highlighted another important point, which is this skin effect that is then important if you change the frequency.
So what you expect, what the maximum increase of the maybe efficiency or angular velocity we can get before we obtain a skin effect?
So we also did some estimates on this skin effect. So for those who are not familiar with it, probably, like the skin effect is the following effect. You have a disk of a certain thickness, d or so, and you penetrate it, or you have a magnetic field, b, that depends on time, and you have some frequency here. And then the thing is, depending on the frequency, the penetration depth of this magnetic field is going to change, and in fact it's going to decrease if you increase the frequency. But we did some estimates, and this skin effect dependence, like it's a fall off that is exponential with the thickness. So if this is the z-axis and this is the magnetic field strength, then it falls off over some distance delta. And in our case, for this 50 hertz frequency, we get a delta of around 1.2 centimeters, but our disk thickness is only 6 millimeters. So we are in a regime where we can neglect this skin effect to first order. But if you increase the frequency at the end, you get a smaller penetration depth, and I think if you double it, it's already
But what exact the frequency when the skin effect starting matter? Can you estimate it, or
so
maybe
yeah, I think this penetration depth is actually proportional to 1 over the AC frequency that you use. So for example, if I would double the AC frequency, I would already be in the regime where, for example, for a 6 millimeter disc, the smaller one that we used in the setup was 6 millimeters, that we could get some effects, but it's not that it would like vanish completely. Yeah.
Well, actually, I think it's proportional to the square root of it. And
Okay.
I think for you can like increase your frequency by 4 times with no any.
Okay, yeah, I mean that's even better, but like qualitatively,
so
that's the behavior that you
okay,
have. Yes.
so from your theory, with this improvement, you can get like 4-time relation to now. So the way you can do it is just taking a transistor and putting it to a DC current and AC regulating current.
Yeah.
So you get the signal with high voltage and a more higher frequency. I think it's
yeah. I mean, we directly use the AC frequency from the power grid, but I think what you're trying to, or what you're saying is that you are using a transistor that switches it on and off, but then what you get is a signal that is not a sine or cosine, but it's like kind of a step function that you would want to kind of smoothen. Yeah.
So what about the phase shift inside ferrite core? Because for me, it's not obvious why it's here.
So we were thinking about this a lot, actually. First of all, like we were just saying, okay, we just need some phase shift somewhere because otherwise we don't get a force because of the symmetries arguments. But what we did then, and where we just measured it and saw that there is a phase shift and we were happy. But we assume that this phase shift comes from the fact that we have this iron core and our coil is wound around it. This, like the coil generates a magnetic field, but then we also induce some eddy currents inside of this iron core. This again generates a magnetic field that is then pointing downwards, and it's phase shifted compared to the original field, as you can see there, like this, it's a small arrow there, and then you add them, and then you get some phase shift compared to the original field, so you will, like in total, get two trigonometric functions that are phase shifted.
Okay, thank you.
I think it's time for clarifying questions from the moderator.
For the reporter, did you just say that the skin effect was negligible?
It's not, no, it's not negligible, but we didn't change the frequency. In our case, at our frequency that we are operating at, it is to a good approximation that negligible.
Okay,
like it's of course like it's suppressing the effect, but yeah.
Can you come back to your conclusion slide?
Yes. Sorry. This one, yes.
Yeah, for the graph in the middle, do you have more than 3 points to see the fit?
These are not fitted curves. These are theoretical predictions and the measurement. But I
Okay,
can
great.
explain why I only have 3 points there. So it's not just laziness.
Could you go back to slide 35, please?
Yes.
And make the video running.
Yes. Sorry.
We're just wondering, so it's not really centered in the...
Yeah, the ball bearing is not perfectly centered, that is true, yes.
And also slide 38, you talk about hitting, but have you noticed it when you touched the... Can you notice the hitting by hand or just theoretical?
I mean, you can notice the heating by hand. This is a theoretical curve, but we also did some more estimates if you were interested later.
Slide 23, you fitted... so you fitted the coefficient from friction.
Yes.
How did you do it?
What
What method did you use?
The experiment was like that. So we had this disk, we made it spin, and then we captured a video from above and tracked the angular velocity.
Yeah.
So that's not with the photodiode, it's with a video.
But like the two coefficient, what method did you use to fit, like to find the gamma and the MC?
Just like a SciPy curve fit.
Hello everyone, my name is Antoine Valentin, and in the name of the French team, I will now be moderating this discussion about eddy current engine. So let's start with a quick reminder of the subject. Make an eddy current engine with an AC voltage source and aluminum disc as in the video. Explain the phenomena, maximize the angular velocity of the disc, and finally maximize the efficiency of the engine. So first, we will go over the reporter overview. Basically, you gave a very, very good qualitative explanation of this phenomenon, mainly thanks to a comparison with an already existing eddy current engine called the shaded AC engine. And you explained that the phase shift is actually very important for the movement to occur. You also gave a proof of the similarity between your setup and the shaded engine, and you studied the influence of a few parameters, namely the ratio and the phase shift. And you also gave an estimation of the friction in the stationary regime. And this enabled you overall to have a good prediction of the angular velocity, and you found that it matched very well with your experimental data. Moving to the experimental data, you only used one disk, an eddy current engine with only one disk, because you thought that this would maximize the angular velocity. You reproduced you had a reproducible magnetic field, and you measured the phase shift. And when it came to the maximization, you basically used a shading code in order to create the phase shift, and you also chose the optimal magnetic field for the efficiency. Moving on to the opponent's overview, you highlighted a few very important trends, namely the nice understanding of the phenomenon, the impressive rotational speed that it achieved at the end of the presentation, and you also studied that they also studied the limits of the setup and the influence of the radius. You also proposed a few improvement points that were very interesting, namely when it comes to the optimization. For instance, you talked about the characteristics of the disk, you talk about the AC frequency, which was not covered by Switzerland. You also spoke of other types of signal, and you spoke of the disk displacement. You also wanted to discuss efficiency versus velocity, and you found a few limitations, namely for the skin effect, the induction, and friction. Moving on to the question that you addressed, you spoke of frequency, which was very nice. You also had the opportunity to speak a little bit of skin effect, which appeared to be negligible, and also you gave an intuitive understanding of why we have a phase shift. For the points to discuss, we still have this point that you didn't evoke, which is the practical problem when it comes to high voltage and to high frequency. And to go further, I have a few points to cover, namely the difference with the original setup, the influence of other relevant parameters that were covered, the efficiency in the transitory regime, and the explanation in the difference of speed between the two disks. I now invite you to join me on stage so we can continue this discussion. And since I guess that we could continue with what the IPT team suggested, which is the practical problem with high voltage and high frequency. Maybe the reporter can tell us what he found was a problem, and the opponent can tell us what he thinks about it.
What you mean was the problem? So with the high frequency, we decided to go with the frequency from the power grid, because I think these devices where you can generate a very high frequency and a high voltage at the same time, and therefore also high current, it's quite difficult to do. So we went with this, with the constant frequency source.
I think you're talking about the point which was mentioned on my slide, but we didn't discuss it, about when you go to higher frequencies, the efficiency of the current generators are dropped down by increasing induction. And on high frequencies, you can't produce the really high voltage, but I think for the setup of the reporter, it's not a relevant question. And the discussion about skin effect is enough. Okay?
So I think probably it's important to highlight that these efficiency curves here, there are theoretical calculations depending on the magnetic field amplitude that we have, and that's also what we measure in the experiment. This is not taking into account any losses that we have, for example, in the coil that is generating the magnetic field. So it's assuming that we have a magnetic field, and then we calculate the efficiency. I also have some estimates for when we take everything into account, and also some measurements if you're interested.
But I wonder, is it really your efficiency like 0.4%?
Yes.
But as I know, for real industrial eddy current motor, it's like 60%.
60% for an eddy current motor? Like, okay, also if you do the experiment in the lab, and I mean, you see that the thing heats up like crazy. It's the voltage that you use to power these is around like 150 volts approximately. So at the end, you reach power. So this is a power measurement that we did. And this voltage range corresponds to the fields where we got into the saturation regime. And as you can see, the power is like 300 watts. But at the end, it's like you have a hard time to get the disk rotating at all. Like the efficiency is really, really, really bad.
Great, I think that this point is covered. Maybe we can move on to the optimization part, because you studied a few important parameters, but maybe then there are other parameters. Right now I can think, for instance, of the choice of the material of the disk, what could be the ideal conductivity, and maybe the opponent can think of other relevant parameters. So maybe you can tell us what you think is important to discuss and what you think are the relevant parameters.
Well, actually, I think the one important parameter of the disk is a phase shift, which is generated with inductive currents. And could you say which phase will be with like superconductor?
Yeah,
I
so
think it's very interesting.
So the conductivity of the plate that we use actually shows up in our expression for the torque, and that means also later in the formula for the asymptotic velocity. So it's proportional to it. So if you increase the conductivity, it's for sure going to increase your angular velocity that you get at the end. So more conductivity is generally better.
But But actually, when you go into superconductivity, there is some like different effect, and it's not allowing the magnetic field going
that is true,
inside, and like you get no phase shift.
That is true. I mean, in superconductors, I'm not sure if this is the place to discuss it, but you have this London penetration depth that material is superconducting, the magnetic field is not going to penetrate. You have these shielding currents around your superconductor, and they will keep the magnetic field out. So you're right, the engine wouldn't work for a superconductor, actually, yes.
Just before we move to another point, which is how the optimization changes when we are in the original setup, I would like to give would like to allow the IPT team to speak.
I just want to clarify, you have a great experiment when you actually measure a phase shift, and then you propose in your theory a model where this is a parameter. Is this the same parameter, or and I believe you use this as a fit parameter, or what does this phi actually mean? Are they different or
So this phase shift phi is a measurement that we did. So we did it for, probably I can show this slide again. I think for example, we also measured this phases phi for the 2-disk setup. We also measured it for the setup with this iron core that we proposed by just using these pickup coils. So that allowed us to calculate the magnetic field amplitude and also calculate the phase shift. So this is not a fitting parameter in that case.
Okay, but can you estimate the phase shift with the theory you have provided on our discussion?
So if you want to treat this ferromagnetic core, theoretically, I think you cannot really do something analytical. I think you would go to some simulations. We didn't really quantitatively describe this phase shift. But at the end, we were able to manipulate the phase shift using this shading coil, and I think for a shading coil, it's actually doable theoretically also. Yeah.
Okay.
We also have a question from the French team.
So your theory is very nice, but I've seen that in your experiment there is a huge displacement of the center of your motor, engine. So don't you lose a lot of energy actually in that? And I'm quite surprised even that you get such efficiency if you have these losses. I mean.
So I think you're referring to that video of the disk spinning inside of this ball bearing. Yeah, exactly, this video. Of course, we have a lot of losses, but these losses, because we measured these friction constants with these fits that I showed you, these losses will exactly be kind of hidden in these friction constants that we measured, and that explains why at the end the fits that we get are pretty good, because it's just described, or we use the experimental input.
Okay. And talking about optimization, you mentioned that the heat dissipation is very high, and maybe it's a good idea to reduce it using the same method which is used in transformators by separating the material with dielectrics.
Yeah, that's a very, very, very good idea. So this iron core that we used was just pure iron. But what one could do is, instead of having this iron core like this, just as a bulk material, you could laminate it, so have some kind of insulators in between, so that would the eddy currents would confine these eddy currents to smaller regions that would reduce the dissipation, as well as for a disk. I think you proposed in your moderation.
You wanted to answer?
Yes, but actually I was talking about disks, because you mentioned that the most heat dissipation in it. So I'm wondering, would it work? Because we need these currents to engine going. So is it possible or not? I'm not sure about that.
So that's a bit more difficult to answer probably, but I think you're right, because we need these eddy currents, so we shouldn't confine them to very, very small regions. But I think one would have to adapt the theory then, because now we are assuming that the conductivity is completely isotropic in the disk, but one could probably model the conductivity as position dependent and get some more insights into that. Yes.
We only have 20 seconds left. Maybe the IPT team can give us their last question.
Yeah, and just for the quick one, you see I understand all the problems of the experimental setup. I understand why the efficiency is fairly low, but what is the main source of such a low efficiency? Is it friction or heat? Can you get to 100% with similar setup?
So the main source of dissipation is definitely heat of the eddy currents. So thank you for that nice discussion, both for the moderator and also the opponent. So at first we discussed this skin effect a little bit, so the impact of what the frequency actually has on our setup. And that is not super beneficial to have super high frequencies, but it would be better to have a frequency that is a little bit higher than 50 Hertz, which is what we use in the experiment. Then we talked a little bit about the phase shift and where it arises from in this iron core. I gave a qualitative explanation and said that, okay, to quantitatively do this, we would need some simulations. At the end, we also discussed the efficiency, and I explained why it's so low, and I think the most relevant source is actually heat that is generated by these eddy currents. We also talked about optimization of other parameters like conductivity, and we talked a little bit about superconductors, which is also interesting, of course. And then, we talked a bit about how we measured this phase shift in the experiment, and then at the end we talked about laminated cores and how this could improve the efficiency of our engine. Thank you.
Now it's time for questions of the jury. Let's start now with Frederick.
Yes, what is the definition of small gamma in the model?
So the definition of small gamma is it's just a ratio between the amplitudes that we have for our magnetic fields. Like we have two positions for the magnetic fields, and we measure their amplitude and we just take the ratio of them. So it's like B1 over B2.
Okay, thank you. And another question, what did you do to optimize the thickness of the discs? Do you have data or theory there?
So we didn't change the thickness of the discs, but having a thicker disc is usually better to some extent, because then you just have more bulk material where you can have eddy currents that are present there, and that would increase the torques that you get in the system.
Thank you.
But we didn't change the thickness. Yes.
Thank you.
So this is a question to the opponent. You had a lot of points about how this work could be expanded. In your opinion, to what percentage was this solution satisfactory? Like, to what percentage has this problem been solved?
Well, actually, I think the big part of percentage, like 40% of the problem was about the ferrite core, because when we were investigating the problem, we stumbled across with the same video and just didn't get what's happening. I think with the other optimizations, it's like plus 20%, but I think the optimization of the frequency, one of the interesting, so like 60 or 70% was covered.
Thank you.
I'd like to ask the reporter what experimental method you would suggest to test your explanation on the phase shift.
The explanation of the phase shift itself?
Yes.
So, of course, I mean, we manipulated this phase shift, and I think you saw in these graphs when we were plotting the angular velocity, like this asymptotic angular velocity depending on the phase shift, that we were able to actually increase this angular velocity depending on the phase shift, and these curves are actually theoretical predictions. So what we did, or I can give some historical background on how this happened. So first we had this green measurement there, and then we thought, okay, we are a little bit off from the maximum, so we want to change the phase. And if we change the phase, we can measure how much we change it. So we just wound around like this shading coil there, and that allowed us to move a little bit more towards this maximum phase shift. And as you can see, also the velocity increased. So I think that's already a good indication of that this changes something.
Yeah, I understand that it does change. So that's the basis of this effect. But why does the phase shift occur? That's my question.
Why the phase shift occurs in the first place?
Yes, and how do you test that your assumption is right?
I mean, I think it's a little bit hard to, for example, measure these eddy currents inside of this iron core.
What does it depend on? Or how would you make an experiment like that? What material dependency there might be?
Like it for sure depends on the conductivity of this iron core that you have. Then I think you can also probably associate kind of an effective inductivity to this iron core, like it's somehow like a coil, you would model this like that and probably do some experiments. Or also, probably one could also measure the AC susceptibility of the thing, but I'm not sure if that would give that much insight.
Sorry.
Did you use other literature than Feynman?
What do you mean?
Did you use any other literature than the Feynman books?
No, I didn't. Like this, we took the phenomenological description from Feynman, but actually we came up with it before. But
Cool. On page 29, are you happy with the quality of your feed, especially regarding the last 3 points?
No, I'm not. So especially with the upper curve, I'm not happy, and I think the reason for this is so that this is where we try to apply the theory that we wrote down that is more suitable for the setup with the iron core for this other setup. And I think what's happening there is that these magnetic fields are not that well confined if you don't have this iron core, so they're more spread out. So I think that's the reason why the scaling doesn't really translate to this setup. And yes.
Thank you.
To the reporter, I would like to explore a bit more this analogy between the two systems, because when you have the two disks, of course, you have a lot of geometrical parameters like the relative radius, thicknesses of the disk. How do you bring that into your theory? What is the parameter and how the intuition comes to you?
So I think what changes, or are you asking mainly about the geometry probably, for example? Yeah. So if you have two disks and you have this coil here, what I think what would have to do is to make the geometric equivalences exact is to investigate these overlapping regions and their area, and I think that would then connect to this gamma ratio that we found, because you have some certain amount of magnetic field, and depending on how you change the geometry, you change these amplitudes of the magnetic field that you can associate to these two poles, and that would be the mapping to the theory that we wrote down to make this a little bit more precise then.
Okay, maybe very quickly, on slide 34 you had the beta R as function of R. What exactly is this beta?
This is this effective reduction due to boundary effects that we had. So if you move closer to the edge, you assume that there are some boundary effects that reduce this coupling, and so you get a reduction of that. So it's in 0-1 interval. Yeah.
Thank you.
I'm a little bit lost in the qualitative explanation. Can you go to slide 21, I think? So these are the currents, the edge currents. What are these arrows?
As these arrows are just there to illustrate this force density that we get at the end. So this shading is kind of supposed to say, or that we have a magnetic field with some spatial gradient here. We also have these currents that are present in this region. And then in this effective area there, we take this cross product and calculate the force density, integrate it over it.
So how are the edge currents how are the edge currents that you are generating there to create this force?
So the theory relies heavily on some simplifications that we did. So the theory is not capturing these boundary conditions, and that's also why we have this suppression factor at the end, because you're overestimating the effect at the end.
Yeah, no, but just a feeling. These are the edge currents that you are having, like this, that will create the force, right?
Yeah. Yeah, I mean, we also did some simulations to get a better understanding of it. Probably I can show them here.
Yeah.
Of course, you have to conserve current, and so these are some simulations that we did. For example, that's how the edge currents look precisely. For example, so that was to kind of validate the theory and get a little bit more intuition about these edge currents.
Where is the disk? Where is this? Is
So this is
the currents on the disk, right?
Yeah, it's a bit.
Those are the magnetic fields.
It's a bit hard to understand. These are the currents in the disk. So what we assumed for that simulation is that we have kind of a disk, or we didn't model this as kind of being bent, but just as a half plane. Then we placed these two poles here, and then calculated what we would expect for these currents in this region, imposing this boundary condition that you can't have a current flowing out of the boundary. And if the curvature of the disk is not too big, then I think this is a good simulation to do.
Okay, I'm fine.
Okay, Just like a question, do you think you can somehow experimentally measure your efficiency of your engine?
So I think experimentally measuring the efficiency as we defined it in our in the theory. So given the magnetic field, and then we calculate the efficiency from there, that would need, for example, a measurement with a thermal camera or something to quantify how much heat we are actually generating by the eddy currents in the disk. We did these estimates with the power source directly, but that gave us, of course, like lower efficiencies because then we also have the heat in the coil and in the resistors that we used.
Okay, but if you like estimate the heat losses, you could, right?
Sorry?
If you estimate this heat loss, you could calculate experimental efficiency.
In that case, I could also calculate it experimentally, yes. Yeah.
So I think that I need a little bit more convincing that you can actually understand quantitatively the system with two disks, because what you did, you had a toy model that has one disk, two poles which are shifted in phase. So this is a different configuration of magnetic fields possessing the same qualitative properties, but quantitatively it seems to me that it doesn't address the problem directly. So also I think, and also there were some approximations and simplifications, like you said, the model with a half plate or a one-dimensional attenuation of the magnetic field in the disk. So in your opinion, how much this affects the overall conclusion, or to be more specific, once you've studied your toy model, how much would you be able to say quantitatively about the actual system with two disks?
So this is a very, very fair point. So I think what we lose if we go to the system with the two disks is mainly geometric parameters. So for example, these locations of the disks are not super well included in there, and also this approximation that we say we have two poles and we just linearly interpolate between them is also affecting, for example, an overall scaling. But what I think is more or less universal is this asymptotic behavior, so the shape of these functions depending on the magnetic field that we apply. I think that's something that is that very well kind of translates to the other system, except for this one fit.
So you're saying that you can understand the limiting behavior of velocity, but if you were predict the behavior of a two-disk system, a one-disk toy model is insufficient.
Yeah, I would say I couldn't predict the precise value because it's geometry dependent. In the end, then you get some scalings that you lose, or some factors. Yeah.
All right, thank you. Jury, you have 1 minute to decide your grades. Okay, I think the jury is ready. Let's start maybe with Christoph. Maybe you are one of the edges of a grade, so.
So I think that this is evident from my question that I don't think that the problem is fully solved. And then the quantitative question is what is the extent that the system that you solved is the system that was in the problem. So I think that's the main concern affecting the grade. And I would like to praise the opposition because I think that Maxim chose a road which was not obvious to me at the very beginning, but it was not about delving into the problems with the solution, but exploring positively what was done in the solution. So I very much appreciated that because in this way a very meaningful discussion ensued, and it wasn't about pointing out obvious deficiencies.
Okay, so I wouldn't be so harsh as Christoph. I think it was nice work in the presentation. I did have some questions after the presentation, and I think the opponent did a very good job here because I had 5 questions and then you had all 5 of them in your slide. So I think really good job from your side. For the report, I really like the theory part. I feel like you were missing a bit, just playing a bit more with the experiment to see okay, now I have this setup, it works, what can I get out of this setup? And I was kind of missing this part, and I understand if you're more a theory person, I am also. And for the moderator, I think you did a nice job. I just feel like you brought some very good points, you even mentioned them during the discussion, but then you didn't come back to them, and you didn't actually allow people to discuss them. But other than that, was good.
Yeah, I like the report a lot. I like the setup you made easy calculations, so I like that, more simple. I would like a better trying to get really how the force is getting there, okay? For the discussion, I thought the discussion was a bit stuck. I couldn't see the points that I want resolved, so. So I lost a little bit in there. Yeah, that's it.
I overall enjoyed very much the fight in general. I think it was a very nice discussion to observe as well. I would like to say that, again, because of the constraint that you're making to your model, I mean, you can see from my question, I was missing a little bit one thing that is kind of like the disks themselves, because, well, if you're simplifying the way that you do, of course it loses information, or it has to be mapped out somehow, right? And for example, in the video of the problem statement, you have very different thicknesses of the disks, very extreme cases. So, I mean, of course, maybe it's too difficult to do theoretically, but maybe you could have explored it a bit more instrumentally to give some intuition how far you could bring, or if it's not important at all for the efficiency.
I think the presentation was put together very neatly. So I really liked how you gradually built up the understanding of the audience, although there were some practical stuff with the fitting and things that we had to discuss later on. And I think the moderator did a good job not interrupting when the physics was getting interesting. So I really like that, and also congratulations to the opposition for the good points and the curveballs.
Yes, so for me, I really agree with, I didn't feel like the problem was solved. The exact video with the disks and different positions, I don't know at this point why, and I really missed this explanation on the phase shift in the presentation itself. It's a good thing that the opponent brought it up. For the opponent, I felt like the whole topic on frequency was getting too long, and you had so many good points on your slides, but you didn't get to it because you discussed too much on the frequency. And yeah, other than that, thank you, it was amazing.
I would say that it was a very well put visually presentation. At the end of this presentation, I think a lot of the audience may have been more enlightened to what we are describing here, especially the animations and the little slideshows it's easy to bury all this stuff into equations and just skip it over. For the discussion that came later, we saw this interplay between explicitly analytical and explicitly theoretical and explicitly representative situations. And I think here is where the opponent, in my opinion, signed, because you were very well studied into the problem, and it was obvious that you had the knowledge to support your arguments. I will agree a bit with my previous jury members that maybe at points we tried to falter, but I could understand where this discussion was leading to. And for that I have to commend the moderator. I don't know what the opinion of the other juries is, but for me I think that the moderator was a quiet force. There were not a lot of need for you to interrupt the discussion a lot of times. So you let it flow where it was flowing, and you decided at points that maybe this is getting too much and we shift a little bit. So I think that this was a huge improvement in flow of discussion compared to the previous fight. And I commend all of you, and I commend also the reporter for standing and discussing with the opponent at a higher level even.
Yes, so when it comes to doing experimental work, there is a fine line between doing it in a controlled, reproducible way and just studying a different phenomenon. But I think your version was a creative and interesting solution, even if it was maybe a bit simpler than the problem stated. So I was fine with that. I would really have liked to see the variation in the thickness of the disk, also because there's a lot of physics there. If you get a factor of 3 more, which is doable, you start getting into this regime of skin depth effects. And in terms of the phase shift, I think someone mentioning Lane's law would really have helped this idea that induced currents tend to oppose changes in the magnetic flux. So as you ramp up the field, that will be slower when it passes through these eddy currents. That would have improved the qualitative discussion, but a lot of things were done very well in this solution. Thank you for that.
Thank you very much. Now I will announce 10 minutes break, but we start exactly in 10 minutes. Don't try me, please. I'm chess arbiter, and I will start in 10 minutes. Thank you. the 10 minutes is out.
Well, we're gonna start now. Oh, everyone, to start. Let's move it from 2:30 to 2:30. So we need to be on schedule, please. It is time to start the last round of this fight. Team IPT will have 5 minutes to prepare.
Hi. Can you check this thing? Yes, it was.
It was connected with the computer.
Okay. Hello, dear members of IPT. Today I will be presenting the problem number 11, Cosmic Skyscraper from the team Empirica, team IPT. So in this problem, we need to investigate how the cosmic rays pass through the building, and we need to develop a method to measure how many floors are above us, and we need to determine the accuracy and relevant parameters of this method. So firstly, let's see from what is the secondary cosmic rays are. The primary cosmic rays that scatter on a target in the atmosphere and create three components: nucleonic, electromagnetic, and muonic one. Let's see more closely what we have at the sea level. At the sea level, we have like this three component, and mostly the initial like intensity consists of a muonic and electromagnetic component, and nucleonic is 0 at sea level. And this muonic electromagnetic component corresponds one to each other, like 1 to 2. So let's see more closely what we see in our components. As for muonic one, we found an article from which we got an energy spectrum for muons, and we slightly replotted it for better visualization. So now we have an energy spectrum of our muons. Secondly, let's see how the muons lose their energy when they pass through material. They lose their energy via ionization and also radiation. So when they pass through material, we can find a coefficient on which they lose their energy depending on the length passed in it. So now we can determine the number of muons. Let's see, we have an energy spectrum of our muons. We have a coefficient in which the muons lose their energy, and now we can exactly calculate how many muons we have after they pass from some amount of material. So let's see what about the electromagnetic component. So we consider it mostly out of photons, and photons decay in an exponential law with the coefficient that corresponds to the material, and that will be later used. So that's like the first part of theoretical work. Let's see what we have done in terms of like our primary preliminary experiments. In our preliminary experiments, we placed Geiger-Müller tubes on a wall, and we placed it on a different distance from the ceiling and from the window. And we wanted to know like what like dependence we have depending on a wall or depending on a distance from the ceiling and a wall and a window. But we got no so good and coherent data, so we thought that we need to know more about like angular distribution of our particles and also about the position of our detector in the building. So we built the next experimental setup. The next experimental setup consists of two planes. Each plane consists of two plates in which we have orthogonally placed Geiger-Müller tubes. And with this setup, we can detect spontaneous events from each tubes in 4 layers. And through that, we can see from which direction the particle actually came. And from which direction the particle actually came. So let's see what we get from our experiment. In our experiment, we get the direction, and we represent it in two components to an x-angle and y-angle. And we plotted the number density function for each direction that we have. And also we normalized it. We normalized it to the all amount of the particles we have on an initial level without a building. So we conducted our experiments in 2 similar buildings and in 2 similar places. That's the result that we get. Also, we measured the intensity outside to know what we are dealing with initially. So also, you can see in these plots that we have a slight change of our distribution, and we have like more particles coming from one side. Let's investigate. That was not random. We placed our detector in this building in such position where we have to the right and to the left building, and to the up we have a building, and to the down we have a wall to the outside. So you can naturally see that when we have a homogeneous building in one direction, we actually have like a homogeneous distribution. But when we have one wall to the outside, we have a slight shift of our peak. So this is naturally because we have some particles that are coming like not directly straight at us, but from the different angles. We'll investigate it later more precisely. So let's analyze what we get from like our distribution. But firstly, let's analyze what we get from the direction upwards in a cone of 2 degrees. In this cone, we estimate that all particles are coming through all material that are above us. So we calculated the intensity of our all particles, taking into account muonic and electromagnetic component, and we estimated them in some proportion. We placed an experiment in one dormitory and fitted this theoretical curve to it, and then we tested it in other dormitory. So as you can see, we get some coherent result, and let's investigate more precisely what we actually like fitted. We had 3 parameters in our theory. So A and B that corresponds to each component, and mu. So A and B are corresponding to component, and this actually like more fit for our detector because it tells us which sensitivity it has for each particle. And they also like pretty like, similar to what we initially estimated. But this is more importantly, it's more about the sensitivity of our detector. And also about the mu. This is the loss energy factor for the photons, and as you can see, it's clearly like matching with the concrete because our buildings are made out of concrete, and moreover, like each slab is around 20 centimeters. So in this problem, there was not only a question on estimating how many floors are above us, but also on with which accuracy we can estimate them. So we calculated the standard deviation for the estimation of our floors, and as you can see, in our estimation we have mainly 3 parameters that are not getting from our intensity function. These 3 parameters are initial flux, the time of exposure, and the square of our field. So let's see. When we get a bigger flux, it's naturally that we can distinguish more floors that above us because the components are decaying, and if we have a bigger flux, we can distinguish them better. And also, if we have a bigger exposure time, we can get more particles that are coming to us, and thus we are also getting a better resolution. As you can see, the theoretical curve is around what we estimated, but also that's like a great result because we achieved experimentally to measure 16 floors above us with an error around 2. That's, I think, maybe a lot. So, I think we could go straight into a conclusion about our methods and what we have actually developed. We developed a method that allows us not only to measure how much floors are above us, but also like distribution of the particles that are coming through, to us. And this method is actually like depends on exposure time, resolution angle, and on the building geometry. But more exactly, for this method to work, we need to know some parameters of our building. We need to know like the material of which the building made and the thickness. Clearly, that is not the approach for every building, but when we are knowing some initial parameters, we can estimate more precisely what we are seeing. And also, if we are talking about different buildings, if we are considering a building, a very tall one, we can estimate the number of floors like not only above us, but maybe in some other direction. And this other direction can be more informative than the top one. Also, as you can see, we clearly made in our presentation that we investigated like the distribution, and from that distribution you actually can reconstruct some profile of the building that you have. And to the end, I would like to thank all the people that was doing this work with me. There was a lot of friends that helped us with the experiments and that worked with us. Thank you.
Clarifying questions from the opponent?
So thank you so much. So first of all, the graph is also here. How did you calculate like the flow using maybe it's not that. I mean, how did you calculate the points here? Yeah.
Here.
So using the whole angle.
No. We for this plot of use
okay, thank you so much.
this angle of cone 2 degrees.
Can you go back to slide 9, please? What are the letters A, B, C, D, and the numbers 3, 4, 3? Sorry,
yes,
5
that
2.
was for better understanding, in my opinion. So, like we have we have 2 plates, and in each plate, so we have like a number of plates A, B, C, D, and in plate A, we now have like the 4th detector that are active. In plate B, we have a 5th detector that now is active. In the plate C and D, we have the number of this number of detector is 2. So, is it answers? Yes. Okay.
Could you go back to slide 5, please?
5?
Yes.
Okay.
So, 5.
Sorry.
What are the different axes like? Why is there a shift of a power of 10 between the 2 axes?
Yeah, this actually acts like for the muon's momentum. That's one moment. So we are considering like the bottom x that is corresponding to the muon momentum. And if you want, we can talk about the energy of our muons later.
Can you go back to slide 8, please?
8, okay.
Okay.
Time of preparation for the opponent. Sure. Time out.
Hello everyone, I'm Tristan from Team France, and I'm really happy to be here today to oppose on cosmic skyscraper tomography. So just to remind you of the subject, we had to develop a method using cosmic rays that can count the number of floors above us and also to characterize the accuracy of this kind of method. So for me, the problem was pretty much solved. Indeed, we had first of all, a really interesting qualitative explanation of the phenomenon. So they explained the cosmic shower and also the choice of muons for the measurement. Also, they dealt with the energy spectrum of the muons arriving at sea level. Also, they explained really pretty neatly how a muon loses energy and how it decays. And also explain how a floor damps, so the rate of muons arriving. They also explained the number of floors and found a source of the inaccuracy coming from the measurement. Also on the quantitative model, it was really well done. So indeed, it was using the energy spectrum, they obtained the real decay of muons and found a formula for the number of floors and also measured the uncertainty of what they did. And so the validity domain is that they assumed that the number of floors wasn't too large, but with the choice of theta between -1 and 1, they could really measure what was up there. And so we would go to a really large number of floors to lose precision. For experimental, so they used a Geiger-Miller tube setup to count the number of muons and to obtain also zenith angle dependency and distribution of the muons, which is really interesting to deal with this problem. They also stacked 4 layers to really measure the different angles, so the one left to right and also the front to behind, so really good. However, even if they varied the number of slabs, I would have loved to see varying, for example, the matter types, for example, using LED to show us what really happens. And also maybe they could be overfitting due to the fact that you only use 2 dormitories built pretty much the same way, so you could lose the generality of the asked in the question. And for the theory verification, so they checked the zenith angle influence that can be also found in literature and corresponds really well. They compared the theoretical prediction with the number of floors, and it worked neatly. And they compared the theoretical uncertainty using the standard deviation on their measurements. So, as I said, they really gave us a thorough insight in muonic physics, so it's really nice. They modeled the attenuation of muon floors, and they gave a way to estimate the number of floors. But theoretically, I would also have liked to see how you model a slabs of floor. How do your detectors actually work, and how do they differ from other setups used, such as this scintillator, and also to look at also the arriving flux of muon depending on the zenith angle, but also above, outside the building to see the cos squared distribution. So the main discussion points we'd like to go through. So first of all, we'd like to just talk about muonic physics a little bit and the use of the Geiger counter. So do you really only measure muons, or are there also other charged particles that come through and get measured by your setup that wouldn't be damped by the floors? Also, I would like to talk about the arriving flow outside. Does it vary between the days? How did you fix it? And also, so to talk a bit about the energy spectrum, that might be interesting to really nice follow-up in the experimental case. So first of all, uncertainty, does it also come from the composition of a slab? So how did you, what distribution did you choose for the composition of a slab? Did you only assume it's concrete, or did you assume that it also contained, for example, metal from the pipes or other components unexpected, like wood tables, people in it? Also to discuss about the worst case scenario when you don't have any information, you're just in the floor, you have to give an answer. And lastly, can we imagine muonic spectroscopy using the energy spectrum? So I invite the reporter on stage.
So thank you for your question. Thank you for your questions. I would like to start an answer with the first one take that was during your speech. You said that we summarize like our flux, but we don't really like for this analysis. We don't really like summarize. We measure in a cone of 2 degrees, as you could see here. But here actually. One moment. Here, actually, on these diagrams, we don't also summarize the flux. We like consider flux in each direction. And about like the measurements, we measure not only the muons, we measure like 2 components of muons and electromagnetic. And electromagnetic mainly consists in our solution of photons. So
you're able to discriminate them using the counters.
One more time.
You're able to discriminate both of these components using the Geiger counter?
We don't discriminate. We count them as whole. Like we don't discriminate them. That's not necessary in our theoretical model.
So thank you so much. I think that answers the first question about the muonic physics I wanted to precise. Also, you during your measurement, how did you consider the outside flow arriving?
So outside flow?
Like how what's the normal count of the...
Okay, maybe this will answer a question. So we actually like measure the stationarity of the background radiation, if you mean that. Thanks to our friend, he provides the data for a long period, like 10 days. And as you can see, the background radiation is remained nearly stationary.
Thank you so much. And do you know what it could depend on? Like where the uncertainty might come from for the
yeah,
radiation?
That's really like the uncertainties can come from the sun flares and so on, sun flares.
Okay.
During our experiments, we especially like search on the sites if there are any sun flares. There was nothing.
I'm really sorry to point that out, but mostly the variation comes from the meteo, so barometric possibility. Also, the most protons that come into the atmosphere that then get decayed on the cosmic shower we talked about don't really come from the sun. But
this is like a part of a cosmic rays, but they then correspond to free component, and we have on the sea level only 2 that we like investigate. Or maybe also like you had a question about maybe why we are using our distribution, and maybe I can clarify. So in the experiment we like measured on different floors, and we measured also an outside intensity, and we proposed a transmissional function that can tell us the difference in the flux. And from this transitional function, actually, we can estimate the number of slabs from each direction.
Assuming they are in concrete?
Yes.
Assuming that they are in concrete? Or,
yes, assuming they're like made from the same material. But usually in a building, like the slabs are really made from the same material. And assuming that you can calculate how many slabs are in each direction.
But yeah, do you think there could be a way? Imagine you're in a building you don't know. You have your setup with you. Do you think there's a way in which you could find the best approximation using the measurement you did really well? So how could you sum up to...
Yeah, yes, actually, like we calibrated for the sensitivity for our detector, yes. And for the different building, there will be a different things that hide inside the number of muons and number of electromagnetic components, so photons. And we can change the mu factor in the photons, and in muons we can change like the coefficient for the energy losses that are coming from the passing through material, and that's how we can estimate.
But so you have an uncertainty on that coming from the literature. So you have an uncertainty on the mu.
Yes.
From the literature. But to go further, so it was indeed really interesting to find the distribution considering the angle, because it gives really nice insights of what's happening. So what do you think you could extract from the method? Do you think you could really scan a building, find how it is done just by getting the measurement, like as I said, in a room you don't know about.
Okay, so. Okay.
We'll continue this, but time for clarification questions of the moderator.
I have a quick question. What was usually the measurement time you did to get these data in the plot? Is it on the order of hours, or is it on the order of minutes, hours, or days?
No. This measurement was for one dormitory it was 1 day long, and for other 8 hours long, as I remember correctly.
Okay, and can you quickly go to slide 4?
Okay. Here
yes,
is it.
This curve. What is this flat part?
Yeah.
The flat part in this curve.
I will explain from this. So in the article, actually, they said that the muons below this. So for the muons below some specific energy, we have a plateau. So that's why we estimate it like that. Okay.
Okay, thank you.
Slide 10, please.
Okay. This one?
Yes. So when you show the loss curves for the different materials.
Loss curves?
Yeah, you have the losses for different energies in logarithmic scale.
You mean
yes,
that's
here.
not a loss curve, that's like the distribution of energy of muons? Okay.
Yes. Did you use, are these the curves you used for your materials of the slabs, or did you use something else for the concrete?
You mean for muons for losses? Yes. We use the coefficient for the concrete as I showed, like when we fitted our theory, like here. So this one, and we got like this one.
Thank you. And on the conclusion slide, please.
Okay.
Just give it up, please, for a moment. Oh.
Sorry.
Okay, I will start and my colleagues will figure this out. Thank you so much for the reporter and the opposition for this great discussion so far on the problem number 11, the cosmic skycrab from Wolfie. I'm Silvan from Team Switzerland and will be the moderator for this discussion. So I will show you the problem statement. I think it was really good solved. I think the two main key factors about it is to determine the many floors and how accurate the method is. And I think we can expand on this a little bit more later. So a quick outline on the report. I think the opponent already gave a good summary on it. She explained us how the muons and the other cosmic rays actually come down to the ground. And she showed us how they get attenuated in different materials and how this will be relevant for later to measure the floor number above us. Then they showed us their setup where they use a Geiger-Müller tubes, which they arrange in a grating so that they can basically have a pixel detector and can detect from where the muons come from, which I think is a really cool idea how to do it. Yes, and then they did the measurements, and they could, I think, if I remember correctly, in the end, predict up to 2 floors correctly and up to 16 floors above you. And I think they showed ideas how to use the angular distribution to measure the building profile, which I also want to talk about later. So let's quickly summarize the speech of the reporter. I think he gave a very qualitative explanation. He thought that the reporter did a great job about the qualitative explanation and also the quantitative model, that the energy losses were correctly attributed, and also he addressed the source of the inaccuracy ever assessed. What he thinks still needs improvement is the influence of the zenith angle onto the muon losses. And also he's really interested on the how the modeling changes if you don't have concrete slabs, but for example another material. He also pointed out that maybe different architectures could be interesting and that there's not so much. So what I think is also that these are very good points, and I think we could go on to the accuracy discussion in the further discussion. So for the discussion, a quick outline. They talked about which particles are detected, thought about what could change, what variations there are in the muons during the day. I think the rest we can't take. I think for the further discussion, I think for the first part, I have only one quick thing, and this is I want to quickly clarify for the audience what the Geiger-Müller tube actually counts, because not all of us are particle physicists. And I think then I want to continue with the discussion on the accuracy, and importantly on what the angular distribution of your measurement can actually give you in information for measuring the floors above you. And then I think maybe if you have more time, we can look at uncertainties doing exposure time or something else. So I think you can both come up to the floor, and I think it would be really nice if you have, in 3 sentences or so, describe what the Geiger-Müller tube is and what measurement it does.
So like a Geiger-Müller tube is a tube inside which you have gas. Usually in our actually is argon and I forgot the name of another one. So like when the particle hits us with the energy that is enough to create an excitement inside the tube, this produces like an electricity. And we need like minimum energy for it to activate. Okay, and also the second blind.
Do you see charged particles only or particles?
So in our setup, we have in this this Geiger-Müller tubes helps us to detect like photons. That is not like charge.
Okay, I think that is enough for this part. I think
okay.
I think the discussion you had before we stopped was very interesting, and I think you could continue on what information you could extract from the angular distribution.
Also, like you said about the outside initial flux that we have, and I should mention that yes, this thing is important to consider. For example, because we actually have a change of 1 moment. I couldn't. So we had a change of flux. And this change of flux is really significant if we consider like the high buildings. For example, if you're considering buildings at a distance around 12 or 13 kilometers above us, but if you're considering like buildings that are a lot smaller, for example, like not considering that the places are on ground level, I think that the initial flux is pretty much the same. But if you're considering like the flux on a 12 or 13 kilometer, that could be like playing a role. Like we measure this.
It's a beautiful graph
with our friends. Yes.
So yeah, you pointed out the discussion about accuracy, and indeed. So just to come back to the what I call the worst case scenario, let's imagine you're in a room, a random building, and you want to know the number of floors, but you're not in your dormitory, so you don't know that it's concrete, you don't know the thickness of the slab, you don't know the incoming flux. So how do you quantify, and where does the inaccuracies will come from, and how do you quantify them?
So actually, I don't really have an accuracy estimation for this method, but actually from the information that you can get like right now from your distribution is like amount of material that you have passed, that your particle have passed, and estimating like the material, you can like show it, and from that the further calculation gets. So as you can see, we also from this transmission function we not only estimated the number of floors of each direction, but also the like amount of material, and this is only thing that we can correctly estimate if we don't know like anything about the building except like the material maybe.
But maybe, let's imagine that you find a distribution for the different expected values for the thickness, the mu coefficient in different buildings. For example, you try to find the distribution on which you'll find an uncertainty, but you have a mean. And using that mean, you'll be able to to really control, like to find to plot your formula with the mean values and gain the uncertainty that will be quite big, about, for example, 1/4, 25%, but still you'll be able to provide an answer. And where do you think that most of the inaccuracy will come from if we do that?
So in this really method, we need to know the material, because it's like not really clear how to estimate it in another way.
Do you, maybe for the report, an idea how you could maybe calibrate your setup, your measurement to get the floor spacing, or what material you have?
A little answer.
Okay, so how to estimate the floor spacing?
How the energy loss in one floor.
Energy loss in one floor from...
So that you can calculate back the number of floors.
So experimentally, if we're talking about, like, if we have an experiment that I conducted before, when you placed your setup near the wall, one wall that is led to the outside, you can maybe geometrically estimate the height of your floor, and then you can estimate the number of losses that you have in one floor, and then you can calculate the number of floors totally, maybe.
So the zenithal measure that you did indeed is really incredible. And what do you think if you had better precision on the measurement, because you only have a discrete number of Geiger counter, but let's imagine that you'll be able to really map completely the distribution perfectly. Do you think you'll be able, for example, to find little peaks due to the passage from one floor to another when you get back like that?
So that's really interesting, because when the particles passing through the floors, they don't only lose their energy, but they only scatter. And the scattering can be estimated. For example, we have an initial flux, and this initial flux, from one floor, we have some deviation of the particles. And this initial flux can be estimated as the Gauss distribution, and the we can calculate the standard deviation for the particles that are scattering, and thus we can calculate the particles, how our distribution really flows in terms of the error. And from that, I don't really think that, answering your question, from that I don't really think that we be able to see such small things, because we have this effect of scattering, but it doesn't really affect a lot of much our distribution.
You lose precision due to the scattering that would make vanish the little precision of your measurement.
Yes.
Okay.
I think we talked about this part. No, I think the idea is really cool, but you think that the accuracy is not good enough. So we have a question from France here.
Yes, very quickly. So Geiger Miller counters detect also gamma rays and X-rays and alpha and beta particles. So when you have multiple stacked, how do you know that when you detect a coincidence, it is a mu1? Or do you take that into account? That's my question, basically.
So literally, we are not detecting on the muons, we are detecting the particles that have enough energy to pass through the full tube spontaneously. When we are considering, we mainly think that our component is corresponding to the muon part and the photons. And if you're talking about maybe electrons, they decay really fast in the first floor of building. Yeah. And also from our estimation, you can see also that the photons also decay pretty much quickly, and we have at 10 floors surely mostly the muonic component.
If it's indeed Geiger counter are low pressure gas tubes that are ionized, so they don't stop much muons, as we can see from the Beth formula, for example, that describe the loss of energy of a charged particle going through a material. So the issue I have is that when you're doing the measurement outside, you're not stopping the electrons and other particles, so you'll have a much bigger measurement than after just one floor, where the electrons and everything else will have disappeared. So I think there's a little problem with that.
yes, we can consider electrons, but not in our theory and assumption, and we talking about the electrons is not a big really component, and this prediction is fits quite well. Okay.
Very little time left, and I want to ask one last question for the both of you. And this is, if you need to improve the accuracy of your measurement, what would you change in one word?
With this setup or at all?
One moment.
Maybe.
It's okay.
Maybe the resolution. Okay, the resolution of our counters. And the time of the measurement, but if we are talking about the setup, the resolution.
Thank you very much.
Okay. Thank you. So I want to thank the moderator and opponent to letting me talk about my problem more. And as you can see, we measured really a lot of things, and I think you can say that we really did tomography of a building, because we can determine the amount of floors in different directions. And I think that this problem is really a beautiful one, and as you can see, the huge number of people worked in solving it. Thank you all, and also the translation.
Time for the jury questions. Let's start now with Christoph.
I would like you to tell a little bit more about certain accuracies. For example, the threshold for the Geiger counter. Is there the background of 1.4 MeV potassium 40 or 2.6 MeV thallium-208? So a natural radioactivity that's going to limit your sensitivity. How do you measure the angle within 1 degree with your setup? And if you are faced with the inverse problem, so even if you have a measurement in a known building and you just have some counts, it seems to me that the last plot that you're showing down in the middle tells us that there is a limited information about the number of floors that you can get. So even if in a familiar environment with a reasonable exposure time, like say 8 hours like you did, what's the actual accuracy in a known material? And I understand that we have to take a unit, so let's assume that we know what's the thickness of the concrete in the ceiling, because your experiment just measures the integrated path of the charged particle.
So the first question about the accuracy of one angle. As I showed before, we plotted our plots, and when I said, do you talking about this graph that we are taking into assumption the cone of 2 degrees? Okay, yes. So we replotted it. We plotted our measurements, and I meant that we are getting 2 degree angle from these measurements. So that's not an accuracy of 2 degrees, because the accuracy is more about geometric one, the square on the top that we get, a square on the bottom that we get. So that was taken 2 degrees in this plot, answering that. And about the accuracy,
natural radioactivity, is it important in your measurement?
You mean?
No, you've got potassium 40 everywhere. That produces a 1.4 MeV line, and that's in principle counted by your experiment, unless it has a higher threshold. And the same for the 2.6 thallium line.
Sorry, it's a little bit too fast. Maybe my team can help.
No, I welcome team members to answer.
Yes, okay.
Mike.
I believe this natural radiation is, for example, so of course we can. It may differ from place to place. If you mean that, that's a great question, because I wanted to answer that we have this constant radiation as we have shown in the back slides.
Artyom, just to specify, I mean the natural radiation that doesn't depend on the number of floors above us.
Yeah, but still, we measure, and it's the constant shift, I believe. That's, I believe, the answer.
maybe you don't get four activation of four tubes for just natural radiation, and for particles you have. So we can distinguish the natural radiation from the particles.
I actually have a question for the opponent. So you had a point about including this zenith angle in your consideration. Can you elaborate a bit more?
I'm sorry, there's been background noise. I didn't catch the
Sorry?
question.
So you had a point in your speech about including the zenith angle in the treatment of the experiment.
They did it actually. So the zenith angle, by what I meant is the measurement they did with the angular dependency coming of muons.
Yeah,
So
yeah, okay,
I put it in there, but they talked about it. So
all right, sorry, then I missed this, because I was just wondering, because this experiment lasts for a long time, so then the angle changes, no?
For me, what happens that using the 3D setup they use, they are able to really map the muons coming from a certain range of angles, and they get this distribution if they wait long enough to be sure they have a great time of measurement. So.
Maybe I can clarify your question. You are talking about like the radiation is really pretty much stationary of all time. So the like distribution of particles that are coming are stationary. But about the zenith angle change, maybe you are considering more like the zenith angle of our distribution that we're getting after the particles have passed through the building. No.
I think I got my answer from the opponent. I was just confused what exactly you were asking, but now I understand. Thank you.
So could you do a 3D tomography image of the building with your setup, a crude one? Do you think it's a tomography gets like you a 3D image taking X-rays for many angles? Could you do you think it's possible to do with a setup?
So like
even better like that, just yeah.
So like if you're talking really about the tomography of getting inside the building and knowing like how the building is structured inside, I don't really, we couldn't really make an image and make really like a lot of these assumptions, but we could estimate the number of material that our particle passes, this image, and like this is what I consider like a more tomography, but not like a real 3D image of our building.
So it has been done, for example, with the pyramids, with the micromegas detector. They were able to tell that there is something in there because they knew the composition of the pyramid and they knew the expected range of value if there really wasn't anything in there. But they use really more precise that really more expensive setup. But yeah, another idea to find the composition of a floor, the material might be, but it's really complicated to try to do energy spectroscopy with the muon. So you can detect but not using Geiger counter. I mean, I'm not sure that we can using them, but it might be an interesting idea to look at the effect on the energy spectrum of different materials.
Maybe a question for the opponent, since he just mentioned this idea of doing muon spectroscopy. How do you expect interaction of the muons to go with the material so that you can extract information?
That's the issue. It's very complicated. It has been shown in the presentation at the beginning that the loss of energy. So, BET formula that shows the loss of energy as a function of the thickness is like that, and the little peak here depends on the density of the material. So, for example, for another material, it might be here. So the effect on the global energy spectrum might be different in function. For example, if you use concrete, there might be, for example, we have like the energy spectrum. There might be something happening at some energy values, but it's really complicated to really look because the precision needed is huge, and there's the scattering as it had been mentioned. But it might be an idea for further physics. But yeah, it's really complicated.
Maybe very, very briefly for the reporter, what is the main parameter of your setup? Number of the arrays or something that you would change to improve more accuracy from what you did, let's say?
So if you are considering that our step that we have to get more accuracy, I think adding like the number of Google Mirror tubes would be great. But also like you can shift the plates a little bit. They wouldn't really they wouldn't really affect like accuracy. Maybe it would get it larger, but you get like a larger angle, and you can estimate maybe some different things, and for different buildings, maybe it would be interesting.
So my question is regarding your detector also. So I would like you to assess the dead zones. So you have a discrete array, what happens where you cannot detect, and also the dead time, so the recovery time of the Geiger-Müller counter. Does it affect your measurement?
So like, yes, we have a little bit between the tubes because they're like under 400 volts. So yes, when the particle like comes through the through this gap, it doesn't really like influence a lot because because when we like have a Geiger-Müller tube, the particles that are coming through this direction, it not surely activates it. So like we can estimate that when the particle coming through that they are not counted. Like we have really dead zones, but if we're considering like the accuracy of our method when we have one square here and one square here, so we are considering like the range of the direction from which particle comes. So that's why you see this number density function, as I call them, heat maps.
Okay, and another question, if I imagine like a tube and I cut it at different angles, I think that the cross-section gets bigger, so does the accuracy depend on the angle? I haven't slept for 5 days, it's a naive question, but does it depend on the angle?
So accuracy depends on an angle at which particle came to the Geiger-Müller tube. So as I told before, yeah, this really happens when you are considering that not all particles that are coming can excite it, because for this thing they have less time, and for example for this particle they have more time. But our like in our setup we have Geiger-Müller tubes placed horizontally, and when we are talking about like the particles that are coming directly above us, we have pretty much the same distance for each tube. So, and if we're considering that we are taking into account only 4 spontaneous activations, so for each Geiger-Müller tube, for each direction, it's pretty much the same.
Thank you.
My question would be also about the setup. So it was a nice setup. I'm interested in where did you get the design from and the electronics? Is that?
That is actually like, I think, the setup that was created by my friend Nikita. He is here. So he really just thought about it, and yeah, we had a lot of Geiger tubes from the USSR, so we thought, okay, we build it.
And also the electronics part, how you process the signals, how you find the coincidences.
Okay, yes, I don't really have an electric scheme, but I can explain. So we had here the Geiger-Müller tubes that are connected to the plate that's called ESP32. If I'm correct, yeah, the 8 in each plane, so 8 by 4 is 33. So we have 43 gates, and on each gate, when the excitement is in the tube, we had what's called we had so electricity flowing through this part, and we register it on a no, we have a voltage change. So and when it's flowing, we register the signal on the plate, and then from this plate we see like what really is happening in the system. Like we process this like so. We had an activation, and we are placing the number of counter, and we are placing the time. And when we have like really small spontaneous activations, that's like happening when we are when we are considering our time discretization. But the time discretization is really like small, so this is like more spontaneous events. I think it's more complicated to answer one question.
I think that's
but okay.
Since it's the final round, I think I will ask a bit of a lighter question. I saw there this nice video with the balloon where you got the height dependency on the flow, right? Could you tell us a little bit about how you did that experiment?
Yeah, so I want, I think, to tell more about this experiment. So our friends did such thing when they created a setup of Geiger-Müller tubes that are circular, and they are finding out from which angle the particle comes. And they created a helium balloon, so aerostat, and they sent it to the atmosphere, and they saw like how the flux and the distribution of our particles, of our radiation is changing through the atmosphere. So that was the just for fun experiment, and we take it into our presentation.
I was also going to ask about the balloon.
So while the jury decide the marks, I encourage everyone to go and have lunch. No, oh, not encourage. You must go and have lunch, okay? Please, try to do it as quietly as possible.
Woo-hoo.